Okay.
Oh, you're on. But he's not. So 9:05.
Okay, welcome back to day 2 of the Linux Security Summit North America. So we have another round of talks today. Apologies for the streaming delay yesterday. Hopefully that will be recorded and be available later. We had BOFs sessions last night. There was an SE Linux discussion and I believe a IMA discussion. I'm not sure if there'll be any this afternoon, as a lot of people will be wanting to get to the airport and travel. But if there are, certainly write them up on the board. So I don't really have much to update today. Again, thanks to everyone for attending, both online and here, and all of the organisers from the Linux Foundation and the sponsors and the program committee. We'll start the first talk. Will be unprivileged access control in AppArmor, and we will wait until it goes to 9:05 so that we sync up with the streaming.
Okay, are we live? Yep. All right, I'm John Johansson, and my cohort is just down here. We're going to talk about unprivileged access control in AppArmor, and specifically application-directed unprivileged access control. User-directed is a whole nother ball of wax. So by application-directed, I mean the application is defining the policy. And the advantage here is so that it can be dynamic, because the application knows things that an outside Mac doesn't know. So basically, think about sandboxing. There's different reasons that you see sandboxing, right? Privilege separation, reduced privilege. It's nothing new. There's been lots of other work on this. SetU has been used in the past to do it, but that's got some privileged things. The OpenBSD, Pledge and Unveil, SecComp does some stuff like this. Unprivileged user namespaces and bind mounts, landlock. So why AppArmor? So our policy is the same, right? So we got a basic API. And the why AppArmor part comes down to, because it's been something we've been wanting to do for a long time. Some design decisions actually were made around this years and years ago. We have a basic API. It just lets you define a profile and tell that in your code, and then tell the AppArmor that you want to confine your application with it. Really, confine is just a simple wrapper around, we're going to compile that policy, and then we are going to load it into the kernel. The compile part it's a wrapper around our parser stuff, compiler. Right now it's very crude. It's very much a work in progress still. And the reason we use the compiler, we have to have this library, is AppArmor uses a state machine. And the state machine was designed a long time ago to be very bounded. And so that we could verify it, it's much simpler than, say, BPF. So it can be verified safe for a user to load stuff, with some other restrictions on it. But so the compiler is going to convert whatever's there into the state machine. So it's just text policy in the application generally, and then you load it, and that's got the bounding and runtime guarantees. Compiling also makes sure you don't have errors, instead of, like, say, Pledge or Unveil, which actually feeds stuff into the kernel, and then they can throw an error back from the kernel. So, like, our binaries policy, you can do that, right? You don't actually have to have text. You could have pre-compiled binaries and just load it. It's not dynamic, though, so it kind of defeats the purpose of using putting it in the application. So once it's loaded into the kernel, like we've verified it, and we can update it unless it gets locked. It's applied to at the process level. And that API we saw is very simple. It's static. Again, it's not very interesting from an application point of view. It has its place, but there's a dynamic API. So this is where, for applications where you start seeing what you want. It lets you expand the policy, so you can start with a basic policy, and then you can add rules to it. So you create your base policy, whatever, and then you can add rules as you need them. And then you can tell it to confine application. And then even after confining, as long as you haven't locked it out, you can update it some more. So for example, here, application's updating it with a rule for argv1, so some file that was passed in, and then it's going to load it up and confine itself with that extra bit. You can lock that policy. It's done on the kernel side, and so once it's locked, that updating of the profile is not going to happen anymore. You can actually add some new restrictions through stacking, and we'll get into that in a bit. And it's done through a flag saying that this is immutable, because it's just all profiles. So kernel side. Of course, users loading into the kernel. Again, we have the state machine, so we are bounding it there, but you also have to be careful about, you want to be able to say, I want to be able to disable this. Not every user necessarily needs to be able to use it, or should be able to use it. Or maybe if there's a bug there that you want to be able to disable it at the system level. We need to control memory, so there needs to be some memory controls on this, so a user can't just DOS the kernel memory. And again, it's verified. It's deterministic. It has very well-defined runtime bounds based on input, and and the user can't control the jumps. It's all set out, well controlled there. And of course, it's going to apply to the children. So dealing with processes, this is a pain in the butt. Kernel deals with tasks. And tasks get their own cred, right? And the threads are just a task that's sharing some of the data. So what we're talking about for a thread is we're going to talk about treat the thread as a process group. And with each task getting its own cred type thing, or when you do updates, because in the kernel, the task updates its own cred, it can cause problems. So what we could do is we could say, we're only going to allow from user space to confine something if you are only single threaded, right? That's not so good. It's, there's a lot of multi-threaded applications, and part of the target here is Pledge and Unveil, and they actually require that you be able to update threaded applications, because those applications have already been updated to work that way. So it's a little bit of a pain. We can fix that by there's a couple ways. We can do it in user space, we can do it in the kernel. In user space, if we did like an early init, users could do it in manual encode. We don't want to have the user have to deal with that. The less work the programmer has to do, the better. We can do it via a library with CDORs and whatever. Issue there is, depending on what your threading libraries are and everything, and what your application is, we can't guarantee something like that is going to run before a thread pool. But generally, it's pretty good. Like I said, other languages may create their own libraries. We've had that before, where Go interfaces actually don't use the C wrapper, C wrapper, Go wrapper around the C library. They create their own, and they've ignored some of the stuff, so they break at times. It's just harder to make guarantees on user space. The kernel, you can do it, but there's some overhead if you're doing it as tracking. We'll talk about the tracking in a minute. And there is also, you could do it the seccomp style, where you kind of freeze the task and then run through, and that's a real pain as well. So right now we are primarily doing by the CTORs and whatever, where we flag a task that it's going to be using application policy, so there's no overhead on applications that don't. But once that's flagged, it is tracked in the kernel the same way as if we were tracking everything. So there can be cases where it could be over a little bit, and we can actually track everything if we just do a config. So tracking, it's, process has a task, it gets its cred, it points to our label, and we've got an unconfined profile, right? When you clone a thread within that process, you get two tasks. Sometimes they share a cred, sometimes they don't, but they end up both pointing to our label. And then they don't always they don't have to share, but again, like I said, they can point to the same label. Fork, when you're doing a new process, we're going to get a split, And generally speaking, the label can be different processes, different applications, different confinement, whatever. That's okay. So we can have them share as well, and that can be inherited. So this is controlled by exec rules. It's not that complicated, and well, okay, it is, but it's just part of regular app armor policy, right? We do this all the time. But with these things, we want a little bit more control over it. So when we enter confinement, the application, so it runs through in the order, right? So 1 is we're loading the new profile in. 2 is we create the cred. 3, we update the structure to point to the new profile. 4, the profile's marked as stale, the old profile, whatever was on the task. And 5, the task is updated to point to the new cred, right? When we have a threaded environment, what's happened is we already have that cred. We have things tracked already. It's basically the same thing, except for the other task, it doesn't get updated right away. So when you go in and enter confinement, the one task enters confinement. The other task doesn't enter the new confinement for the application profile until it enters the LSM hook. We have an update, we check, see that the profile has been made stale, and then it will update itself. And that's what's going on here, is it enters its critical section, it grabs the new label, and then it updates itself. So the creds, the cred of individual threads get updated asynchronously. And we have to have that information there to track, and that's why there's a bit of overhead if we were doing this for every task in the system, because we have a little bit on tasks that are in application confinement where we have a little bit extra work going on clone. Updating confinement is the same idea, right? We can replace the profile. It looks the same as processes, right? It just looks the same as we just did with entering confinement. Under threads, it's looking pretty much the same thing, right? We're just marking it as stale. This is all regular profile replacement for us when we're doing the updating confinement. And that's how we work all this, is it runs like through our regular profile replacement dynamic updates. Not a huge deal, except for the tracking, right? One of the things we do have with exec is we still keep, with application policy, we still keep all of our exec type behaviors and rules. We have a rather rich set of exec behaviors you can do about how you can transition profiles. These application profiles don't generally use them mostly. They just inherit or go unconfined. But they can, in some cases, actually load multiple profiles. We'll get into that with stacking later. And then they can use some of the other transitions. Interface right now, PR control or a syscontrol for this syscall, I mean, because we don't want to use the file interface that we usually use for loading policy. LSM will block that. Our own policy will block that. We couldn't use the LSM syscall because the LSM syscall, well, it's not for loading policy, right? We could create an app armor specific syscall, but for the moment, we're just using a PR control just because it was easier. As we get this in better shape, we may try adding a syscall instead. So introspection is just through the regular LSM interfaces that we're all familiar with. So the proc adder interfaces or through the new LSM syscalls. And what you'll see is this weird /and thing is stacking. That's how we expose it to the label to the user space. And so unconfined and app would be, it's unconfined at system policy level, but we have an application policy on this application So how does it interact with system policy? Well, when we have our application policy, it's always going to be stacked against system policy. So they will both be in effect at the same time. And what that basically means is that application has the intersection of however many profiles are stacked on it. So it could be 2, that's probably the most common, but it could be more than 2. And what it's allowed is just the intersection of all those. Like, so with 3, it would be the middle of, this standard Venn diagram. It's put into its own policy scope. So what this basically means is when you have applications that are interacting, say one process with another, there's things like, say, Unix domain sockets where you're communicating across IPC-wise, and your policy wants to say, this task can talk to this task, this subject can talk to that subject or object, whatever you want to call it. So what this does is it says, being in its own scope, the applications policy doesn't interact or interfere with the system policy. So system policy doesn't have to worry or care that the user policy is in place. You just use system policy, it doesn't change. And that's just showing that, that they can talk to each other. The applications themselves can, at the policy level, the system does at the policy level. So one of the things we have is, okay, we have application policy, but you have to go update your applications, right, to use it. And nobody really is going to do that except for for a few special cases. Part of the motivation here is Pledge and Unveil's been around for a while, and applications have been updated for this already. So can we take and can we map Pledge and Unveil into the AppArmor API? And some of this is also working towards improving the AppArmor side of things as well, so that we can do better, right? And it's a work in progress. How close can we get? It's not going to be 100%, but we can actually, we think we can get pretty close. So Pledge, that's the Pledge syscall that you get from OpenBSD. It has a set of promises and exec promises. Those promises, there's text strings. And those are the current set of promises that BSD lets you make. Each of those has a whole bunch of defined semantics to them. Very interesting when you go through some of these. They're very, if you talk to BSD people, it's like, well, we don't have an exact definition of what they are. We kind of revise them as we test things, and they have revised over time the behaviors of them. It's so updates will have to be made at some point. The set of promises, so it's just, like I said, it's a text string. You list which promises you want to make. The null on the exec promises just means we're not making any exec promises. It's not affected, right? We're not doing anything there. You can't, with Pledge, you can't update, but to add new promises. You can only take away. Once you've pledged something, you are only ever reducing your permissions that you're granting. So in this case, you can't add the Unix promise. But you can go down like that, right? And you can, if you don't put any promises in there, it's an empty string instead of null, that says basically, I don't want to be able to do anything except for basic compute. And how they define it is basically only the exit syscalls allowed. So that's bringing in some syscall level stuff. What we're doing now is we have a little library, and it gives the Pledge Unveil interface. So we take that text string and we parse it in user space, and we convert it into tokens, obviously, and then we convert that into a set of AppArmor rules for each one of those promises. they could be multiple, whoa. They could be multiple promises, or it's just, multiple rules, or it could, in some cases, just be one. Got a second here. Can I get this back? There we go. There we go. And in the case for development purposes, we actually are allowing us to call out and have some user space rules defined. So we can include those in and update without having to recompile this library. We can do some revisions. It just allows us to tweak and improve stuff without, easy as development. Eventually, those are going to have to be all folded back in and not allowed, because if you think about pledge and unveil and stuff, some of those pledges stuff, then you can't get out to these even. You can't include the external files. We don't have a perfect mapping, like I said. Pledge uses stuff that is, some things map really well to the LSM, but not the syscall level, right? We are looking at bringing some seccomp in to help with making this a better, more accurate emulation of pledge. But we'll see. The seccomp side is interesting in itself. So one of the things we have to do to try to get closer to pledge is, like I said, we've been working on revising AppArmor, updating it, and extending it. So breaking promises in pledge, the defined behavior is you get a sig abort, and the application gets killed. That's not generally how AppArmor works. We generally do return E access. So a little bit different there. We do have a flag that you can set on profiles to kill flags, and to kill processes if they violate rules. It's normally sig kill and not sig abort. But we've added the ability to set the flag so the profile can change, or the signal, so the profile can change what signal is going to get sent. So that would get us to the sig abort side of things. Except we're not always sig abort with pledge. There is the exec promise and the error promise. So the error promise turns all the other promises into returning errors instead of signals. That's not too hard to handle in the mapping. The parse just recognizes that we have an error, and then we don't set the signal, the kill flag. Exec's harder because exec isn't not the kill signal ever. It is an eno-sys. So lots of fun there. Again, not AppArmor's normal behavior. So in this case, we actually have added the ability to set, and that was the error behavior too, right? Exec's a little different, but error, when you set the error pledge, it's not e-access, it's eno-sys. So we've made it so you can set the error code that's going to be returned. E-access is the behavior for exec. So no kill, not eno-sys, you get e-access. Kind of a pain. So this is some of the work that has not landed yet. We're working on it. So what we've gone here is to give us more flexibility instead of just a global profile flag, being able to set these on a per rule basis. So now we can control and say, if I want to kill on this set of rules, I can do that. If I want to air out on these set of rules, I can do that. And the priority stuff will let the compiler know if things overlap, which one's important, how they overlap, when they overlap, where to resolve what. And even the error code sort of can be set. The reality is you only can have 2 of them. but it can be set which one you're using at the rule level. So that gets us all the combinations for pledge. It's very much still a work in progress. So what does it look like? Right now, pledge on BSD, we'll use like last.com. We don't actually work with last.com, right? Or not last.com, last.com. It'll set a P on it for applications that had the pledge. We don't work with that right now, so we're just working through regular introspection. What you'll see is, again, you'll see stacking, right? You see the system profile is unconfined, and then you see P. We're just following what pledge does there. It uses P and U, so you see a P on the application. And we haven't looked at extending, like Serenity OS has a proc, proc Unveil and something else for pledge. That are other extensions, ways to introspect that we haven't looked at yet. So pledge exec, unless you set an exec promise, is usually what it is it's what we would call a UX, so transition to unconfined. So we're going to drop the application profile, and then basically you go back to being just system profiles if the exec's allowed like that. When you have an exec promise, that changes the behavior. What happens is we change the application profile to do what we call a CX. That CX takes a second profile that's loaded with the pledge profile that handles the exec privilege or exec promise, and we now transition to that on exec. So it's kind of like a regular AppArmor policy transition. We just have set it up so that the two go together when we build profiles. Promise reduction. So we mentioned that pledge can only ever reduce, right? And we talked about the AppArmor API allows, until you lock it, allows you to increase your privilege. So how do we do this? We want the promise reduction to only ever, we want guarantees on it, right? But we also need to allow updating in a sense, because we want to reduce what you're allowed. So to guarantee that, to make that guarantee, we want the guarantee to come from the kernel. And so how do we do this? We're not doing it through profile generation in user space. So we set the immutable flag on our profile that we're putting in pledge to guarantee that you can't replace it, can't update it. What we end up doing is we start doing some stacking to do this right now. This is not ideal. So every time you reduce your promises, you get an extra pledge profile. And you get the intersection of them. So as you could technically increase your promises, except for user space will try to reject that. But even if you manage to do that, you still, at your kernel side, get that guarantee. You get the intersection of them, and it only ever reduces. It looks ugly and gets worse as it gets longer on the introspection. And there's a little bit of a runtime cost to it, too, because regularly an AppArmor profile, when we compile it, we optimize it, and it's the same amount of time to match 1,000 rules as a single rule. Where here, because it's dynamic, the more profiles you have, that's 3 profiles worth walking, right? So there's a linear cost to it there as well for the matching. We don't want to do that. That's kind of what you would see on the introspection, right? P and P and P. So we're working on moving to Boolean conditionals. And so what happens here is we're going to lock the profile, but we're going to allow some Boolean variables that are exposed and allow user space to toggle those Boolean variables. And this is going to give us our promise reduction. What happens is the right to access the Boolean variable is tied inside the Boolean variable conditional. And so you have to be able to set that Boolean variable, you have to have it already. And once you have it and drop it, then you can't access it again. And then it takes away the rules as well. And this can be done at runtime. And so this is some of the work that's going on right now, is to add these Boolean conditionals to this. And so we can just have a single profile and have that performance. And then it changes the way we have to do the update of the library, but that's not a big deal. It's all hidden. So Unveil. This one, when you look at it first, is it seems like it's easier to map to AppArmor. It's all about the file system. AppArmor tends to like files. And what it is, you specify a path, and then you specify some permissions. And the permissions are just R, W, X, and C for create. And it's a straight mapping on the error code that it returns back, so e-access. That's nice. It's mostly anyways, it's not quite. So it's very easy with Unveil. Once you start doing Unveil, you just can keep adding new promises. So this maps back to the AppArmor API pretty well again. We just add a new rule and load it, and you have access to it. And what Unveil does is Unveil at some point, with directories, you can add directories, and we just map it over directories and file rules, whatever. The directories are expressed as text strings, but they have some interesting properties to them under Unveil, and we'll get into that in a minute. And relative paths, we just map it into a variable. Same thing on the directory. How do we handle these? There's a couple different ways, whether it's a kernel variable or a user space variable to be worked with. So Unveil, like I said, directories have some interesting behavior. What happens with Unveil is once you do an unveil of a directory, you get everything underneath it. So that's kind of the tree, right? The whole directory tree underneath. You have access, and you have those permissions that you specified, sort of. Unless you make another unveil that is different than and more specific than the other directory. So then you get a different subset. This is actually hard to express in AppArmor at the moment. It's possible to do it programmatically, but as you're trying to write AppArmor rules, if you're trying to write an AppArmor rule, this is actually hard to express. We are doing some work to make this easier to express in policy for a human. But interestingly, that one's actually hard for us to express in policy at the moment. So there's some other behaviors with directories that are interesting. So directories added after you make an unveil, even if they're in that area covered by the unveil, are hidden. So this is a different behavior, and we actually don't handle this right now. We have some ideas on how to handle this, but it's one of the areas where we fail on Unveil at the moment, this hidden directory. With Unveil, mappings, again, the null like this means to lock Unveil. So what happens there is we just set the immutable flag and load it up. So it's very much like pledge in that sense. Once you've done that, then you can't replace or update your Unveil profile. Introspecting, again, you'll see instead of the P, you're getting the U. Okay, so let's talk about how we can bring these together. So like I said, you get profiles. So what we're going to do is for pledge, you get a profile. For Unveil, you get a profile, and that can stack with the system profile. The pledge profile can be locked, and the Unveil can be unlocked while it's being updated until your Unveil promise is removed, or you lock it. So we have some different semantics also with pledge and unveil. We talked about them already. SIG-abort versus e-access. The unveil is you're building it up until you lock it down. The pledge, you're locked down and reducing all the way. And we can handle this all at the profile level. And all that is handled at the profile level. So that can coexist within the stack. And so just because you have your profile over on pledge killing things, your unveil profile, if it's doing violations, it will do the e-access behavior. Same with system policies. System policy will behave the way it's supposed to. Yeah, we did those. And then, again, when you have them both, you're going to get your system policy at the introspection. You're going to get your pledge profile. You're going to get your unveil profile all showing up. Again, it's not exactly the same thing as BSD there for introspection, but the regular system Linux interfaces aren't the same as OpenBSD interfaces either. So do we have any questions?
I had a question early on.
Yeah.
I don't know if that's working. What order do they stack in? So is it system first and then followed by application, or application followed by system?
Okay. It's an interesting question, and it will depend. So it's a little more complicated than that. So it's based on policy namespaces. And so policy namespaces are hierarchical. And the first in the hierarchy is going to be the first in the listing. So say your root. And then you can have your next, so like your pledge and unveil or whatever. But the reason I say it's complicated is, say we do a pledge or unveil at the system level, and we've created also a child policy namespace. And that child policy namespace has some other application policy in it, say for a container or something, and that it is doing its own system policy, so say LXD, right? So the system level pledge unveil will show up before the policy that you that's in the container namespace. So it will sort, canonically it sorts based on level of hierarchy, and then it has a canonical text order based on name, and address is the fallback as well.
Hi.
Hi.
Nice talk. I had the sense of déjà vu.
Yeah.
You know, it looks, from my point of view, it looks a lot like Nanlock.
Well, like I said at the beginning, it is something that has been done several times, right? It's a bit like Landlock. It's a bit like Pledge and Unveil. It maps better to Pledge and Unveil than it maps to Landlock. There's some other ones out there as well, right? And like I said, today we're talking specifically about application-directed policy. There's another side to this where the user can have a user policy namespace, and the user can define policy for the user's application that is different than the system policy, and that policy can be loaded and it can be stacked again, and with the application policy, with the system policy. So it's quite a flexible mechanism.
Yeah. Yeah, so that's exactly the goal of Landlock, and that's why you have the same changes. And yeah, I'm sure you took a look at Landlock, so yeah, I was wondering what is the difference. I mean, from an API point of view, yes, there's a difference, but you can implement the same way Unveil and Pledge with just a use-based library using Landlock syscalls. So
you can.
Yeah.
Yes. So, like I said, they each are approaches to it. We want to make sure that, how to put this? We want to make sure that things are available, and we want to make sure it integrates to the system the way we want it to integrate. And we're not against Landlock at all. We are just trying to provide options. And it's a different way to do it. And when I said this has been in the works a long time, some of the decisions around the state machine were actually made back in 2005, 2006 era. with the stated goal of being able to expose this to users. So this has actually kind of been in the work for a very long time.
Okay, so yeah, it will be interesting to see how it goes. And yeah, I'm wondering how it will be received, I mean, mainly upstream of the kernel. So if you need to run new syscall, which I guess you will need to, because
Potentially, it would be either a new syscall or a PR control. Like I said, right now we're just using that. But whether that's the best interface,
yeah, probably not.
Yeah.
Yeah. Second, use PSCT at first, and then
Yes.
edit the dedicated syscall.
Yes.
That's why with Unlock we created new dedicated syscalls.
yes, exactly.
So
But there is also, I mean, from an LSM standpoint, a lot of the LSMs have desired a syscall for a long time. There are operations we have within AppArmor that we would rather have a syscall for, that we have been forced in the past to go through the file system interface. And so some of those have been taken care of by the LSM syscall. So for example, the set proc adder. Others have not. And so it would be very nice for our point of view to be able to load policy through a syscall instead of through the file system interface, because we do have situations where we would like to be able to load policy and without having to mount the security FS into, say, the container.
yeah.
Yeah, and so it's very similar to what's going on with Landlock. There's no question or debate about that, right? It's just a different way of achieving it, and it integrates in with what we were already doing. It's just trying to complete out the model. And there are some use cases where we have, for example, integrating at the AppArmor level, where we would have like a system label where the application policy could say, I want to take the system label and do something based on it, where the system policy doesn't want to interact with the stacked application policy. So there are like I said, there's some system integration bits there. It's just what it is, right? Don't worry about it.
I don't, but and last question. So yeah, well, same goal again. Landlock was designed to be able to implement Unveil with the limitation that you just highlighted, because Linux is not OpenBSD. And so did you take a look? So yeah, in OpenBSD there's like hundreds of application sandbox with Unveil and Pledge.
Right.
Did you try to run, well, I mean, OpenBSD is a whole system providing user space as well.
Right.
And they did a lot of forks of open source projects for OpenBSD.
Yep.
And I think most of the Unveil and Pledge calls are in these forks, not in the upstream open source code, which is used by Linux distro and so on. So I was wondering, yes, in theory, that's a good thing, and I would like to do the same with Landlock. But in practice, it looks like, well, that's not really the same source code. And as you highlighted, the semantic is kind of moving because...
It is, you're right. And that's one of the big problems with the application policy side of things, the unprivileged policy, application policy is the source code gets forked, the semantics between different source code bases drift. So cherry picking patches from BSD, say, into our Linux version of it, you get conflicts, and even if you get it to go in, doesn't mean that it actually is doing what it's supposed to do.
Yeah.
And this is one of the things about developing these promises, is they have to be tweaked. And one part of the work of this is trying to come out with a good set of mapping, trying to run different things and get a mapping that is good for most of them, because it's going to be a little bit different on Linux than it is on BSD. And even on BSD, like your different versions of BSD, those promises actually change what they do because they've been refining them themselves. You're right, it's a problem. But it's better for applications for us to try to take, like Pledge and Unveil, than say use our API, right? Our API is there. There's a few cases where it'll get used, but that API is more flexible. But in reality, it's only going to be used in a few special cases.
Yeah, well, most of the Pledge and Unveil patches were written by OpenBSD developers. I mean,
Yep.
core developers, so not generic application developers. But yeah. Well, that would be interesting to see how it goes.
Yeah.
And last thing, just remember that, in fact, there's already an Unveil library implementing Unveil for Linux with
Yes.
comp and landlock. So did you think about contributing to this library?
So we have looked at it a little bit. Will we contribute to it? Possibly. We're, how to put it? Where we can probably get work mostly for this is in picking patches into applications for Pledge and Unveil. So we have people who are interested in getting Pledge and Unveil in the Linux application base. Those patches for those specific applications, and so that's one of the places where there will be contribution for landlock as well, because there's more applications that use Pledge and Unveil on Linux. That also works for landlock's Pledge and Unveil, right? Can we contribute to those libraries? Possibly. I can't promise anything. Anything work time related to that, right? Could it be personal time? Possibly.
Okay, thank you.
All right. Anything else?
Yeah, I just had a quick
Yeah.
comment around the syscall discussion. And I know we've kind of talked about this a little bit. So initially, we have 3 LSM syscalls right now. None of them, like you said, are anything that would be suitable for loading policy. But just because we have these 3 now doesn't mean we can't expand that list in the future. So, maybe it makes sense for it to be an AppArmor specific system call, but there's a number of LSMs which load policy. If we wanted to create an LSM policy loading syscall, I think that would be a reasonable discussion to have. The LSM system calls are not limited to just the 3 that we have today.
Correct. Like I said, PR control for now because it's easy, and where we go from there, I do expect it's going to be a syscall, but the syscall, well, that's how that goes, right? That takes a long time to design, and there'll be a lot of back and forth on stuff like that. All right. Well, thank you.
Am I, okay, oh, great. Well, thank you very much. I'm about to, okay, here we go, we're getting started. Okay. Gotta do something here. There we go. Hello, I'm Casey Schaufler. I'm going to be talking a bit about some work we're doing with regard to a library for LSM using applications. If you don't know me, I've been doing operating systems for a long time. I've been doing security for a long time. I'm the author of the Linux security module. I'm currently working on LSM infrastructure primarily, and I'm a hobbyist, which means I get to do it when I want to and under what conditions I want to. So we can't really talk about a library for dealing with Linux security modules until we've actually talked a little bit about Linux security modules, so we'll just dive into this a bit here. Linux security modules provide additional restrictions to the normal system policies. Now, they've been around for long enough that a lot of us think of those as normal system policies these days, but it really is an attempt to have a general mechanism for having additional controls. And traditionally we've used, this was initially mandatory access control was where it was initially focused. Today though, we're using it for sandboxes and we're doing some hardening work in it. Yama is a good example of some of the hardening we've done with it. Sandboxes, we've got landlock, and for mandatory access control, SE Linux, AppArmor. And AppArmor is now going to be doing some sandboxing too, so we've got a good collection here of additional restrictions that you can have with the normal system policies. Now, sometimes when you want to do something different, or you need to introduce some additional attributes. If you're doing mandatory access control, for example, you might want to have a label on a file. If you're doing integrity measurements, you might want to have a hash of some sort associated with a file or a process. So there are all kinds of attributes you could add. Timestamps, all kinds of things. And you're going to put those attributes on all kinds of things. You're going to put them on processes, files, other system objects, and things that are not objects. Port number, ports, for example. You might want to put a security label on a port or do an integrity measurement on a tape drive for some reason. But there are all kinds of attributes you might want to put on that are specific to your security module. And sometimes you're going to want to access those. So if you want to see previous talk, we had PS-Z to tell you the attributes on a process. Well, you might want to do that for administration purposes. If it's a sandbox, you might want to allow your user to modify those attributes. If you're a program like dbus, you might want to look at some of these attributes to decide whether to deliver messages from one process to another. So there are all kinds of things that you might want to use this information for, and you might want to get it into user space, and you need a way to do that. Now, traditionally, back in the bad old days, before 6.8, you do the administration via special file system entries. SE Linux FS, Mac FS, Security FS, are all mechanisms you can use to administer the LSM. So examples here. You can see that, we can use Security FS to look at the list of security modules on the system, and use SMAC-FS to look at one of the network configuration values. We can also do process attribute manipulation and identification using proc self-adder. There are several entries here. Some LSMs use all of them. Some use one of them. Some use none of them. So we can look at look at the information about my current process, looking at these interfaces. And that's fine if you're in a shell script, but it's really not very convenient for an application to use. So very recently, we added LSM system calls. These are relatively new. But the problem we've got with these is they're not in the library anywhere. We have 3 system calls. One will list the security modules that are available on the system. Interesting factoid here, I don't have a slide for it, which I probably should, is that we introduced the whole notion of having an LSM ID, which is a numeric value, which identifies the security module in addition to the name. And this makes the interfaces a whole lot easier. You don't like interfaces where you have to pass 2 strings. The name and the value, that's really inconvenient because either you end up parsing it, and parsing is bad. So we've introduced LSM IDs. Another system call will get an attribute for the current process, and it will. You can either tell it to just give me one of them, or just give me the first one, or give me the one I've specified, or you get the whole list of all of the attributes with that ID that are associated with that process. So if you have AppArmor and SE Linux at the same time, you'll get 2 entries, one for each, and they'll be identified so you can know what to do with them. You can also set an attribute, and this has interesting aspects to it because, of course, each LSM may have its own policies regarding whether you can or can't set an attribute. And again, not all LSMs support all attributes. But these are system calls. They're not in libc anywhere. They're not in any library anywhere. So we need to have a library for them. How about liblsm? And that's what we're working on right now so that we can do this. Now, there are a lot of things you're going to want to do in an application with the security module attributes. You're going to want to read them. You might want to print them. You might want to do all kinds of things with them. So we want to make it easy to do this. Not so easy that everybody just, that it just does it for you, but we want to actually make it pretty easy. So we want to do a few things, allow you to do a few things. One of the first things we want to do is to manipulate the LSM context structure. Now, the LSM context structure is the fundamental unit of data that the get and set operations are going to use, rather than having multiple parameters, which makes it really difficult to return more than one, for example, or to specify more than. So this is the basic structure. We've got IDs, flags, lengths of various sorts, and then the actual attribute value itself. This structure it's not difficult to deal with, but boy, it would be really nice if I've got a list of them. I would like to be able to get to the next one in the list. So we're going to have a function here, LSM context next, which is really just going to be adding the length of the current value and returning the pointer to the next one. Some people are afraid of doing pointer arithmetic on their own. And based on some of the casting I've seen when people try to do this, I can sure understand why they're afraid of it. So we want to have a function to do that. We also want to have a function to fill the buffer. One of the reasons for this is that we want the LSM context to be aligned. And calculating the alignment isn't necessarily obvious. So we'll just create the length properly, rather than having the user specify it when they're filling the buffer. That makes it pretty easy. So I mentioned a little bit earlier that we have ID mappings. So if you have a numeric ID, you'll sometimes want the name if you're going to print it. If you're interpreting a command line, you probably want somebody to specify the security module by name rather than number, because nobody really wants to remember that SE Linux is LSM number 100, or that AppArmor is 102. Just hard to do that. So you want to have a function to do that. So we're going to have a function LSM ID to name. It's going to map an ID and give you back the pointer to the name. If you have a name, you're going to want to get an ID from name, so you have the name, it'll give you the ID. You don't have to remember the numbers anymore. Everybody's a lot happier. Now we also have to have IDs for our attributes. So the attributes we currently have are mapped directly to the entries in proc self-adder. So there are 6 entries there, so we have 6 IDs. No reason we couldn't have more. Again, not all LSMs support all of these IDs. But just like with the LSM IDs, you want to have it be able to map it back and forth. Again, pretty simple. Now, everything here is so far really pretty straightforward. But if we're going to have a library, we're going to want it to work everywhere, because we don't want somebody saying in their application, if I have a kernel after 6.8, then I'm going to be able to get this information. Otherwise, I'm going to have to go do a whole bunch of stuff. So we want to do some LSM system called emulation. So we want to be able to go look in the traditional places and pretend we're implementing, you ran the system call when the system call is not there. So we're going to have some new functions for that, of course. The older kernels aren't supporting the system calls, so we're going to have some functions. LSM get self-adder proc, which is going to get it from proc. LSM set self-adder proc, and so forth. So that you don't code your application to use the proc interfaces, you code your application to use the system calls, and if you don't have the system calls, you get the values anyway. Now, /proc has some issues. One of them is that you don't know which LSM is necessarily giving you the value if you look at proc self-adder current. This is my bad. I made the mistake here. But we started looking at ways to address this, and one of the ways we said, well, let's put a subdirectory in for each of the LSMs. And that'll make it easy. If you know you're looking for an SE Linux, you look in SE Linux, but so forth. So we got a subdirectory for SmackIn in version 5.0, AppArmor in 5.8, and the SE Linux maintainers have declined to have a subdirectory. So we're working with this. It does make the emulation just a little bit trickier. Current implementation that we have, we say for Smack we're going to look in the subdirectory. For AppArmor we're going to look in the subdirectory, and we're going to assume that what's in it's not in the subdirectory. That's the SE Linux one. And if you don't have SE Linux, then we have to figure out based on who comes first, which one it's going to be. But we don't care. If it's not SE Linux, we don't care because we have a subdirectory we can look in. Proc also has some privilege issues. While the reading is pretty consistent, updating entries, setting attributes isn't consistent, and not always the same as with set proc adder, and it couldn't be policy dependent. So you can have SE Linux policy that doesn't allow you to update that entry. You can have SMAC policy doesn't allow you to update that entry. You can have SMAC policy that doesn't allow you to update the SE Linux entry. You can have SE, so the emulation is going to be perfect. It's going to be very, very close to similar, but you're not going to be able to have it be identical, and that's a problem with emulation. Again, this is one of the reasons why we went with the system calls, was so we could have a more consistent interface, more consistent behavior. We're going to have to do some things on the systems to actually make use of this now, because we don't have a whole lot of user space that's aware of the fact that you might have multiple security modules. You know, one of the aspects of security modules we really like to have is that, you know, these applications don't really care what the policy, what LSM it's got under it. You know, it's going to be some system call behavior might be a little bit different, but applications are supposed to be able to handle that. There are some applications, however, that actually do depend on the security module, that do have to be aware of it. In fact, on Fedora 39, there are 93 packages with SE Linux in the name, and 157 that depend on libSE Linux. That's a lot more than I expected. With Ubuntu, there are 16 with AppArmor in the name, and 38 that are depending on libappArmor. And there's virtually no overlap. So if you're going to look at this and say, well, I want to make some, you know, make my distribution LSM agnostic, you have a lot of work to do. Just determining which of these actually have issues excuse me, is going to be a bit tricky. Now, most of these things you're probably not going to have to do much with, but on occasion, you're going to have something that's really going to stand out as a whopper. And of course, I'm talking about systemd. Systemd is really very good about being aware of Linux security modules. It does a whole lot of things in support of the various security modules and their various behaviors. So clearly it needs attention. But it probably isn't going to need more than a few tweaks. Now, one thing that is going to have to change is this line of code that's actually in systemd 234, where there's an assertion that you're not running SE Linux and SMAC at the same time. This caused me a considerable amount of vexation during testing on module stacking, where I was like, why won't systemd come up? Oh, because it says this is a bad state. And it turns out there's actually an easy fix for that. And in general, looking at applications, there are easy fixes for most of the things that they're doing that are security module specific. ID-Z, for example, doesn't need to be testing to see if it's got SE Linux enabled, because it refuses to tell you the attribute values if you don't have SE Linux enabled, even though it could. We want to have a few simple commands that are going to map essentially directly to the system calls, so that you can put them into your shell scripts. These are tentative names for it. Having played with it a little bit, underscores in program names are not convenient, so that'll probably get changed at some point. Another aspect of user space that we have to deal with, logging. All right. Most of the logging we're doing is pretty independent of what security module you have, but audit records are an exception. If an audit record, if you've got multiple security modules that have attributes, need to produce them in such a way that you can get all of the attributes, not just the first one, or in the current state, the only one. So we need to have a new audit record type to explain the attribute contents of the various LSMs. That means new audit record type, new audit parsing. It's not difficult. It's known technology, but it's just something that's going to be different here. we don't have to do anything in a library for this. We just have to do that in the audit code. So we got a bunch of things we still have to do. The liblsm current implementation of it is still pretty basic, but there are things more to do. One of them is the peer context. Right now, there are two mechanisms, SO peersec and SCM security, where you can get the value for your peer on a network connection, but you can only get one. And we'd like to provide an LSM context instead. That way you can do it if you've got one, if you've got more than one. We also probably want to have functions for file attributes. So we'd like to be able to say, give me the attributes of on this file, and give me all of them. Setting them as well, rather than dealing with the current. Well, what you have to do currently is you have to go in and deal with the extended attributes directly. Dealing with extended attributes is not very convenient. So if we have this, then we can just do one thing and get that through. So to sum things up, we've got LSM system calls now. We need to have a way to get at them. So we need to provide a library to do that. It'll help us get away from using /proc. Ideally, it'll help us get away from having to know the gory details of how things are implemented with extended attributes. And it should make the entire process of moving applications so that they can be LSM agnostic, so that they can work with all LSMs rather than one in particular. Make that a little bit easier. But it's a balancing act. If you want to, we're going to put out a fairly simple library initially, get some people using it, and then of course they will say, well, why don't you do this as well? At which point we say, well, okay, we'll do that. Extend it out, make it a little better. Or we could wait for everybody to start screaming and doing their own implementations. But being proactive, I think, is a good approach. We can see what happens, carry it forward, and get some good interfaces out there, so people will actually start thinking in terms of doing their applications for LSMs as opposed to for SE Linux or for AppArmor or for SMAC. And that's really all I've got to say about it. I've got a URL here for the current Git. It's not very big, but it has a few things, a few ideas in it. It's even got man pages. Haven't done a man page in a long time. So I think that's about all I've got. So questions? Don't push. Well, if there are no questions, then I think we're on to a break now. Thank you.
Hello, can you hear me? Am I audible? Good morning, everyone. My name is Tushar Sugandhi, and I'm going to talk about IMA log snapshotting today. So welcome to Seattle, those who are traveling from multiple places across the globe. It's a beautiful weather here outside. Okay, so let's get started. A little bit about myself. I've been in software industry for like 15 years, in software security for about 7, and Linux security about 4-ish. I work for Microsoft. That's pretty much it. So let's see what we are going to discuss today. I want to discuss what is the motivation for snapshotting IMA log. It's about kernel memory pressure, long-running devices without reboots, and attestation, server-side processing. We also want to just not snapshot the logs, but we also have to preserve the integrity of the IMA subsystem for remote attestation and we'll discuss what needs to be done from the kernel side to make the feature work, and what needs to be done from the client/service side to make the feature work, and some other design considerations. If demo gods are happy with me, we'll see a demo. Q&A followed by Q&A. Big disclaimer, this has been discussed in the community on the IMA mailing list, and I was fortunate enough yesterday to have a conversation with IMA maintainers, Roberto and Mimi. So I modified a slide a bit to take their feedback into account, but I'm flying the plane as I'm building it. So not everything that I say as part of this presentation would reflect in the final design/documentation. Of course, it will evolve. This is the current state that I'm representing. So let's get into the basics of remote attestation. So imagine you have two parties who are talking across the internet. Alice wants to talk to Bob, and she wants to get some work done from the Bob. But before delegating the work to Bob, she wants to ensure that she can trust Bob. She wants to ensure that Bob is trustworthy. Alice trusts Charlie. Charlie is trusted by Alice. So what happens is Bob sends his information to Charlie for verification, and Charlie vets it and verifies it and sends the verified report to Alice. So this is kind of normal world. In the attestation world, Alice is a relying party, Bob is attestee, and Charlie is verifier/attester. So in cloud era, so you have relying parties, you have attestees, and you have verifiers who are verifying that attestees are trustworthy by checking their various parameters and signals, and then sharing those signals with the relying party so that relying party can trust the attestees. A little bit deeper into the IMA world, as you have seen yesterday, IMA is an integrity measurement architecture. It's a subsystem, it's a kernel subsystem, which monitors events from the kernel side, extends them into PCR, and it has IMA log, which is in the kernel space. So events are recorded into the IMA log, and that IMA log with the signed and TPM PCR codes is the user mode agent sends to the remote verifier. And the TPM PCR codes, since they are signed by TPM, you have a chain of trust and root of trust. So you can trust those codes, and you can replay those entries in IMA log and verify that the log is not tampered with. And then you can validate the values inside the log and make sure that whether it meets your security bar or not. And if everything looks good, you send attestation report in form of tokens, in form of certificates and whatnot, so that which marks that attestation has succeeded. So what is the motivation behind IMA log snapshotting? Currently it's a monolithic log which sits in the kernel. And when we are using it, we observed a few problems, and that's why we are proposing to snapshot it. So obviously, kernel and user mode memory pressure is one of the issue. And the devices that are really running for the long time without getting reboots, so stuff accumulates and we need to deal with that. That is another motivation. And we'll get into these motivations in detail and then. As you know, the verifier sits in the cloud. It is not local. It's not a praise scenario, as Roberto was discussing yesterday. It is attestation, which is outside of the client or the node. So we want to make the remote server-side processing fast. So that's another motivation. So let's dig a little bit deeper into the memory pressure issues. So as I said, IMA log is stored in the kernel memory. And depending on the IMA policy, it can, and the system state, you can generate a lot of events. I mean, it measures various critical data, various disk device mapper block devices coming and going, various file system measurements whenever those files in those file systems are touched. So it generates a lot of data, and it is very valuable data. It is needed for attestation, no doubt about that. But depending on the policy, IMA log can grow. And of course, kernel doesn't flush the IMA log. It is ever growing, because if you flush it, there is a loss of information, and then you cannot replay it on the server side. So, and you cannot validate the tamper-proofness of the log, that it's not tampered with. So it's a genuine good security design that the IMA log is not flushed currently. I'm just repeating what I said here. Yeah, as I said, truncating it would cause irrevocable attestation failures. On the UM side, the user mode side, user mode processes combine various logs. You have boot logs, you have, of course, IME is the runtime log, attestation log. And you have to be, sometimes you have to be consistent with the format which server understands. So there is some processing happens on the server side. So this leads up to multiple copies of IMA log, and you are dealing with a big chunk of IMA log, then there is a memory pressure on some user mode processes as well. That's what we have observed. So together, kernel mode and user mode handling of IMA logs add to the memory pressure of the system, and that leads to the next point, which is long-running devices which are with no reboots. As I said, when IMA log grows, it can only be flushed by the kernel. It's read-only for user mode processes. And in today's cloud era, where the servers are running for a really, really long time, months, sometimes years, no kidding. And we have some industries which depend on these long-running servers, like gaming industry or e-commerce industry or finance, whatever. So even a blip of few seconds, it costs them money. I mean, they just don't accept the grayouts. So to flush the IMA log, to relieve the memory pressure, you can warm reboot, you can cold reboot, but that needs time, and even few seconds of delay is unacceptable. So what can we do here? That's another motivation. So the systems are running for a really long time, IMA log grows, and it is non-trivial both from the security threat model point of view and practicality implementation point of view to recover from that the bloated memory on that node. And the last but not the least, you are sending those logs to the remote attestation server, and the server needs to quickly go through the logs, replay them. You can do seal unseal, that's another story, but if you are doing the replay of the log to match it with the PCR codes, then in that case you need to really quickly respond. So in the current model, it takes time. The more the log grows, it takes time for the server to respond. So that's another motivation to solve this problem. now that we have discussed a few motivations, genuine business cases, what are the solutions that we have thought about? So one is how do you trigger the snapshot? That is one thing that to think of when you are discussing the solutions. Then, of course, you need to persist it, copy it from the kernel memory to some persistent storage or network storage, basically to relieve the memory pressure, but still preserve the information. So how do you do that? And do you need a marker event to logically separate the snapshots per se? It's an optional thing, and we'll get into the details of that. And last but not the least, truncate the in-memory copy of the IMA log. So, of course, and on the client side, you need to, client needs to be aware that the kernel supports snapshotting capabilities, and it needs to interact and pass over those, not just the single IMA file now on, but multiple snapshot files plus the latest instance in the memory of the IMA file. And of course, server needs to be aware that, hey, the clients which are talking to me can not only sending a single monolithic IMA log, but they are sending in-memory IMA log plus some snapshot files. So these are the things that we need to take into account when we are talking about the solutions. So let's dig deeper into each of the things that I talked about. So one, the triggering mechanism. How do you trigger the snapshots? It can be triggered by a user mode agent that is running on the system, and it could be as simple as having a syscall, and it could be a file open, and that triggers the, you can implement that syscall in IMA subsystem and can start trigger of the snapshot. Some kernel mode events like UR kexec soft booting into the new kernel, that can be another logical point where you want to trigger the snapshot. There could be thresholds that can be defined in the IMA policy, and those thresholds can be trigger snapshot after every 10,000 events in the IMA log. And IMA does keep track of number of measurements in the log, or little bit less reliable, but harder to implement thing, but you can keep a track of memory of how much memory has IMA log consumed, and if it reaches certain threshold, and if that threshold hits, then you can say that, hey, trigger the snapshotting. Or it could be a combination of them. There is no reason why multiple snapshot triggers can't be present. So that is about snapshot triggers. As I mentioned, we discussed about the snapshot aggregate / snapshot marker, which logically separates two snapshots. And it can be optional, just a disclaimer, but the goal or the purpose of the snapshot aggregate marker is to make the service side process of the IMA log more efficient, and we'll get into the technical details how. Basically, we can use some events to denote that the snapshot has been taken, and the server can exploit those events to make the server-side processing more efficient. Yeah, a little bit detailed into the aggregate event. It can be a simple empty event with just the event name. Those who are familiar with IMA template, you have event name, event template, event data, and PCR in which you are extending the event and digest and so on and so forth. So you can have just the event name, or you can say that, hey, give me the current timestamp, very cheap and simple, or just keep a counter that how many snapshots have been taken so far and just increment that counter. Or it could be something sophisticated, which aesthetics very expensive, like getting the PCR states from the TPM, and those are eventually used for replay and then calculate the final value. It can be done from the kernel mode, it can be done from the user mode. Maybe doing it from the user mode logically makes sense, doing it from the kernel mode clearly is very expensive, and if we want to go to that route, it needs to be well justified. Maybe we can get away without using this complicated snapshot marker. As I said, it's an optional thing. I mean, things would still work, and we'll see on the service side how we need to be stateful. Anyways, moving forward. So snapshot, trigger mechanism, snapshot, aggregate, marker event. What next? We have persistent storage location. So far, the IMA log has been in security. Well, it's in the kernel memory. And now when you want to move to some persistent location, the relying parties, the agent, you can have different agents running on the node for different purposes. One is for the certificate management, one is for, I don't know, talking to mail server, or there could be one is for OS update agent and whatever. So multiple agents need this information. So the location where the snapshot R needs to be stored needs to be well known. It needs to be standardized. It can be configured by IMA policy. Currently it is not there, but you can have an entry in the IMA policy which says that, hey, this is my storage location for snapshots. And of course, I mean, you can have a kconfig such that the IMA policy stays read-only and it is not appendable at runtime. So it is a robust, secure location. I mean, the path is immutable. The location can disappear, and that's a separate problem. But as long as you have a reliable location, the relying parties can take dependency on that location. And you can do, once you have the location, you can do things like IMA can provide a symlink to be consistent with that location, so that when you are adding, you are referring to the IMA log from its current location, it points to actually location on disk. Or you can use file systems like Fuse, which was recommended by some people in the community when we were having this discussion on the IMA mailing list, that use the file systems to snitch snapshots so that it appears like a single monolithic file, but it is actually multiple files. So these are a few things that we considered when we were designing this feature. So I shared this diagram without snapshotting. Now with snapshotting, you have kernel mode copy of the IMA log, and you have snapshots. So let's play a high-level workflow, how things will work out when on the client. So you on the kernel side, you have an IMA log. Let's say you have event E1 and E2 in the IMA log, and on the user space you have a snapshot file which is currently empty. And this control file, it was earlier part of the discussion, so that's a remnant in my presentation, but we can get away without this control file. So, but for the sake of discussion, let's pretend that we are dealing with this control file. So some of the trigger happens, and once the trigger happens, the snapshot aggregate event gets generated by IMA in the kernel, which can be a PCR digest of extend of event 1 plus event 2, and then you can kernel can copy the event 1 and event 2 from kernel memory to the control file. Technically, it can directly be copied to its final destination on the disk, and that can be done by user mode process as well. And then when user mode says that, hey, I'm done copying, you can finalize it, or you can truncate you can truncate the in-memory events. Then once IMA gets that signal, IMA truncates it, but the snapshot aggregate event stays. So and when the new events come, they can continue appending to the existing in-memory IMA log. So you are left with in-memory portion of the IMA log plus a snapshot. And when you have multiple such triggers happening, then you will accumulate multiple snapshots, but they will be on the disk, not in the kernel memory. So let's talk a little bit about the server-side processing, the stuff that I talked about, the marker event, which I claimed it will help with making the server-side processing more efficient. So let's pretend that on the top side you have a monolithic IMA log with events E1 to E12, and let's see some specific events. You have a device mapper, you have an encrypted disk, and you are loading that disk and resuming that disk. So let's say that is event 8 and event 10. And event 11 is SE Linux policy hash. And by the way, these events are measured in IMA log today. I mean, I was proud to do that work with the critical data and device mapper work. These events can be used to on the server side to say that, hey, does my client meets a specific disk configuration or SE Linux policy hash to trust that client. And in the snapshotting world, let's say you create a snapshot after every 3 events and store it on the disk. So that is the bottom part. So notice that here our marker events are being added, and this is the complicated, sophisticated marker event that I talked about, which has the PCR hash. And as I mentioned earlier, it can be also given on the side by the user mode process. So it doesn't necessarily need to be a part of the IMA log. But for the sake of discussion, let's pretend that it is part of the IMA log. And now on the server side, you are, rather than getting the full monolithic IMA log, you just get the latest copy, truncated copy of the IMA log. And now that we have event 789, it is the starting PCR state for that event. And when you do the replay of the extend operation of for E10, E11, and E12, then you arrive at the same PCR codes, and then you can say that, and only this much information is sufficient for you to validate that this portion of the IMA log was not tampered with. It is signed by TPM, and it is validated by the PCR codes. So if your attestation policy says that I will succeed the attestation if the SE Linux policy hash matches my expected value, then you don't need all these events. Or you say that, hey, my device mapper device needs to have this configuration, but the resume doesn't tell me the sufficient information about that device. So that information is present in the load. So you need to stitch event 10 with event 8. And when the server says that, hey, I only have event 10, where is the event 8? So then it can ask the attestation client, give me one more snapshot from your repository. So then you are just dealing with this snapshot, this snapshot, which is denoted by disk, and the in-memory copy. You don't need the previous 2 events to succeed the attestation. What else? Of course, there are drawbacks. I mean, there is no free lunch, right? You can, so far with the monolithic IMA logs, you just pass the entire log and you don't need to save the state of the clients on the server side. But if we are going with this approach, you are not dealing with seal and seal, but you are doing the replay method for attestation, then you need to preserve some state. And as I mentioned, there are different types of marker. Remember, just the event name and no value, or timestamp, or PCR digest, or the last case snapshot. So what this table on the server side does is it tells whether the client was ever attested. If it was never attested, then the server would say that give me the in-memory one and give me all the snapshot files. Because this was never attested, I can't trust this guy before analyzing each and every event in the IMA log. But if it was attested until some point, which let's say before the presentation, before this presentation started, so you can say that, okay, the events before this were already attested, just give me the snapshot or the in-memory log after this value, and then you should still be able to replay and attest the remaining one, given the previous attestation had succeeded for the older snapshot files, or the PCR digest method, or you can say that I had attested until snapshot 4. So if you are giving me an in-kernel memory IMA log which says that the system is at snapshot 7, then the server would say that, okay, give me 5, 6, and in-memory 7, then I'll be able to do the attestation. So who does what? And this is my earlier push was to try to do everything in kernel so that it is trustworthy, it is measured by IMA. But do we really? I mean, security, and there is always security and efficiency slash doing things quickly, it matters. So efficiency and performance matter, sorry. So taking those things into consideration, the trigger can be either on the server side or on the user mode side. It could be, as I said, it could be a kexec soft boot, or the number of events, or it could be a user mode process poking kernel that, hey, please generate a snapshot. And as I said, snapshot marker event, it can be generated by the kernel, or it can, it's a PCR read, so you can just use the tpm PCR2 command to generate it from the user mode. There could be some synchronization issues, and as I said, it's optional, but it's possible. Copy log is obviously a user mode thing, because you're just transferring the logs from memory to the disk at a predetermined location guided by the IMA policy. But truncate has to be in the kernel, because as I said earlier, the IMA log memory is controlled by IMA subsystem, not the user. User mode can read it, but only with the root access, but it cannot modify it for the security reasons. So truncate has to be performed by kernel. And let's pray that the demo gods are happy with me today. So let's see. I'll first show you. So ASCII runtime measurements and binary runtime measurements, this stuff already exists. Runtime measurement counts is keeps the count of runtime measurements. And this snapshot file is the new thing that we added, as I mentioned, the control file which says that trigger the snapshot. Or you can just have a file system syscall on this, and it will trigger the snapshot. So for this demo, I will use that as an example to trigger the snapshot. So let's see what we have in the ASCII runtime measurements, by the way. Are we good on time? Yeah. So, by the way, is the text legible? You can read it, right? Okay. So boot aggregate being the first entry in the snapshot, and then kernel version is measured, and then you have built-in trusted keys and bunch of other entries. So this is the initial state of the snapshot, of the IMA log. Then let's say we have an agent. Let me open, yes. So as I said, you can trigger, you can copy, you can truncate. So I'm using that snapshot file syscall open call on the snapshot file to trigger the snapshot. So let's trigger it. So okay, I have triggered the snapshot, and let me open another window to show you what's happening. Okay, snapshot aggregate event has been generated in the IMA log, but as you can see, the previous entries are not yet removed because my agent, user mode agent, haven't copied them to some secure location. So let's copy it. I just want to copy it at some default location, and if I go to the default location, there is a on disk IMA log. Of course, it's a binary because servers usually process the binary log. ASCII is for human readability, of course. And then I will instruct the kernel to truncate the IMA log. So there is some glitch, but the IMA log has been truncated, and let's verify that IMA log is truncated. That's it. You have snapshot aggregate, but the previous entries have been removed from the log. I want to thank, of course, Mimi and Roberto for very lively discussion on the mailing list, and of course in person as well, for giving their guidance, feedback, and expertise while designing this stuff. Paul from SLinux, who was also a very huge helping hand in guiding me in the right direction. And Sush, my partner in crime, who was helping with whiteboarding, sound acting as my sounding board, and prototyping some of the stuff. And here are a bunch of references to the mailing list threads that you can go and comment on, or if you want to learn more about this. And of course, this presentation is also present on at this location. And that's it. If you have any questions, I'll be happy to answer.
So generally with something like this, when you're changing what is being measured, you publish a profile for how to appraise the measurements and the collateral that you're generating. Is the only source of that the patch, or do you have that published as a document?
It is not published as an RFC yet. The design/approach was published, and as you can see, I mean, you are fundamentally changing, because if you truncate the IMA log and clients and servers are not yet ready to make use of this feature, so it's a data loss, and the attestation will simply start failing. So it's a disruptive change. Even though it brings benefits, it's a disruptive change. So we wanted to first vet the idea, get the consensus from the community that is it okay to do this? And I think we are getting a consensus that this is needed, this adds value, we should do it. So now it's the right time to send the RFC.
Do you have the attestation verification logic in an open source project, or is that one internal?
You have multiple verifiers in the industry, and some implementations are open source like Keylime and all, and some are internal. So of course, since the functionality is not yet implemented in the kernel, the attestation clients and verifiers are not aware of it, so they can't, there is no code to implement it. So my first focus was on to prove that it is doable and try to do it the kernel side changes first, and then once they are upstreamed. By the way, I mean, if you don't truncate, the stuff should still work as a monolithic log. So clients and servers will have time to adopt this feature. But I don't think clients and verifiers have done the work to make use of this feature, because the feature doesn't yet exist in the kernel.
Thanks.
Sure.
My question is regarding the IMA log. Your first comment about it was that it is not, the kernel does not flush the IMA log. And then a couple of slides later, I saw that the kernel can flush the IMA log. So is that to suggest that the kernel does not automatically flush the IMA log, but it can flush the IMA log manually? Is that what the message was intended to convey?
Okay. So when I said kernel does not flush the IMA log, means that the capability does not exist in the kernel. It just doesn't. There is no way.
Okay.
Unless you warm reboot the system.
Okay.
So because it's a data loss, and if you even modify a single bit in the IMA log, it goes out of sync with PCR digest, and you get PCR mismatch when you are doing that attestation.
Okay.
So what I showed in the demo is the implementation of the proposal, that in order to delete the entries before snapshot, can I do that? And I wrote, Sush wrote the code to demo it can be done, and that's what the demo was.
Okay.
So it is not yet in the kernel. Kernel cannot truncate it.
Okay. And is the amount of memory configurable that the IMA log uses?
IMA log memory is not configurable.
The memory that the kernel memory that it uses?
Currently, it is not configurable. Okay. There are some checks in the IMA code base which says that, hey, don't surpass more than half of the RAM, available RAM.
Okay.
But it is not configurable.
All right. Thank you.
Thank you.
Hey, I had a question about two different operations here. You said trigger that generated the snapshot event, and then copy was to copy that to disk. It seems odd that maybe they're two separate events, because couldn't we get to a situation where if we trigger and some other events were generated before we copied, don't we have an issue right there where the snapshot is a few events back?
That can be handled by truncate, and thanks to the suggestion from Mimi yesterday, that when you are giving the truncate signal, you can say that I have copied until from entry 1 to entry k, so it's safe to delete from 1 to k.
Got it. Okay.
And whatever was, because user mode is not under control of what will get measured and what new entries will get added, right?
Right.
It can only say that confidently that I have copied last k entries, so truncate last k entries. The snapshot can come immediately k plus 1, or it could be k plus y.
Got it. Okay.
Truncate should handle it.
And I haven't kept up with the conversation on the list, but has there been any discussion about maybe a handler? Like trigger being one option, maybe it's kexec, maybe it's just writing one to a file in SecurityFS, but then the option of the action of snapshotting and copying, maybe like the core dump handler, for example. Some process gets registered as being the thing that's going to handle these events being truncated and copied to disk. If there was a specific handler that could be registered at boot time, perhaps some of these operations could be simplified to just the kernel executing this handler, piping all these events through standard in, and letting the handler operate however it wishes?
We started with a lot of complex desires when we proposed it, and if you follow the links on the thread, it went into multiple directions, what clients can do and what servers can do, and consistency and reliability related ones. Okay. But to summarize, it was a very valuable suggestion from the Linux IMA maintainers to keep it simple. And the simplest approach is to just let kernel handle the truncate. That will keep the logic very simple. Rest of the stuff can be done from user mode. The trigger/copy can be handled from user mode. There is a benefit of having multiple triggers and some from the kernel side, like on kexec, and if it reaches certain IMA event counts. But that doesn't really need to happen. You can just assume that, hey, I have copied last k entries. It can be the starting event. Technically, you don't even need a trigger IMA event, but the truncate has to be there. And if you just have truncate, then I think it is still doable.
Okay, thank you.
Sure.
So to answer the question, it was the original design required a lot of locking, and because of the locking, we decided that let's keep it simple and let's prevent additional locking.
Thanks, Mimi. So the locking, the desire behind the locking was to make sure that it is synchronous and no loss of events, but maybe it is not needed. Yeah. I think we are at time. So thank you, everyone, for attending this one and for your questions. Appreciate it.
Zara. She had a visa issue. She was supposed to be here, but could not come, but she did send a pre-record, which we're going to be playing.
Hello, everyone. My name is Zahra. I work for Microsoft on various systems and security projects. And in this talk, I want to discuss some of the ways that we can use large language models for improving kernel bug discovery. And this is not an official Microsoft product. It's mostly discussing some of the ways that we can use them better and some of the challenges that we still need to resolve if we want to get a more automatic ways of like utilization of LLMs for kernel patching or kernel vulnerability discoveries. So let's get started. So as you know, large language models are becoming more and more advanced. And that's why in recent years, we can see the integrations of LLMs in a wide range of like use cases, software stacks, security scenarios for monitoring, for like finding adversarial patterns. And that's like an exciting areas now that like we can integrate LLMs in like different use cases. And one of the reasons for that is that like LLM, like basically the entire software stack and around it, it's becoming more flexible and better and more mature for designing customized model. And I really like this like description of LLMs to like operating system from Andrea Capoditai, that basically it mentions that like even from distribution perspectives, LLMs are becoming more similar to operating systems, because there are closed source LLM models, and there are open source ones that is similar to like Linux, and also all of the components, it's like getting more complex from like all the systems interactions, the file system, caches, like basically like similar to IPC like interactions with other models. So this is a basically exciting time for like designing customized model. So one of the questions that we were looking for like as a use case for LLMs was this question that can we use LLMs for like more automating the patching process on Linux kernel. And the architecture that we were discussing was that like, can we use, for example, the generative adversarial networks, like putting several models for generating a good input for basically before going through the whole patching generator, and these models interact with each other and basically go through this iteration loop to finally create that that patch that can be like deployed, maybe like starting from a small patches. But the question was that like what would be like the this architecture look like? What would be the data, the input that we need to like provide for this, for both the generator and the discriminator. And basically, one of the main problems here that we also were looking for was that can we, as a part of this process, like our before like our generator, also detect that this like code has some vulnerabilities, so that it won't generate like vulnerable patches. So it can find bugs or suspicious patterns, or if it can detect like some of these codes are I don't know, copied from Stack Overflow or some like sources that basically can be marked that should be checked. So the patch, the generated patch won't be like some vulnerable patch that's would be like even worse than not using LLMs at all. So that's why we looked at 3 different ways, different techniques for improving that particular part of the bigger problem of automated patching, to just find out like can we improve like just and make sure that like we have a process for finding some of the bugs, for even like making sure that it knows some of the vulnerability descriptions that we provide, and can it like look for those specific bugs. And so we're going to discuss these three approaches from first the simplest, like prompt engineering plus RAG. That's basically like you're giving more information to your LLM. The second is LLM-based assistant API from OpenAI, and also then I discussed the fine-tuning process on some of the data that with that like it can be useful. So the first step for adding more like information to our LLM is through like prompt engineering and retrieval augmented generation, or RAG. There are several papers that basically focused on this area for vulnerability detections, not specifically on Linux kernel. There is one actually that's on improving the fuzzing. That's basically like integrating LLMs to syscaller, but that's a different story. I don't want to go through the details of that. So we took a look at those papers, like finding like if they have useful suggestion for prompt engineering, and some of the suggestions were useful, such as like describing the vulnerability first, describing the API first, describing the data flows for the code, and these are general like information. Some more were more useful for C, like for example, one of the papers finding was that GPT-3 is mostly like very good with Java, but for C, those recommendations were more helpful. And some other techniques that they suggested, such as like first discussing like the high level like description of the code, and then basically ask the LLM for line by line or function by function investigations. And for our evaluation environment, we started very small with 32 mainstream patches. We picked mainstream patches because they have like already, like we can see like reviewers' opinions, like what is the actual final fix for a bug, and like useful detailed informations of like how the bug is like happened, how you can reproduce it, some like a specific like debugging information. So that's a good source to compare what we can like expect from like a LLM and what we have currently. And the other source was like pure like 15 kernel source code from kernel version 5.19. And some of the like areas that we were working on, like such as SE Linux, IMA, Hyper-V, VSM, and 15 kernel code I picked from those areas. And for RAG to feed like more information to our model, as I mentioned, like the current mainstream patch descriptors are good sources, and some of the security blogs, such as Google Project Zero, for more complex vulnerability, CV details, not much, but a little bit. And this was like basically a small environment to experience design experiments with OpenAI GPT models. So, for example, this patch that's fixing the issue on BPFG, that's basically the problem is that it's that piece of code assumes that like the current process has unconditional access to a page that is always available, but that address, when you size the page and change the page size, it's not available, and it's causing a memory leak and segfault. So basically, when we ask like a model about detecting like any vulnerabilities, memory leak in that piece of code, like unmodified code, not the patch. So the model couldn't detect it, and it was like, no, there is no memory vulnerability here. And then we manually wrote a description that there can be places that there's a specific dependency or assumptions to like an address that may not be available for that current process. Basically, not giving the the whole patch to the model, but a very smaller manual process for describing that this is the high level issue. And then we ask again with this this is our code and what was the problem. And this time, surprisingly well, it describes like exactly what can go wrong. And that's why after that we asked like, can you create a patch for that? And as you can see, it can detect like exactly where that variable should have we should add a condition. So if that's there is a change in the size of that, it could go to have another condition for handling that. That is not the right way of fixing this bug, but as you can see, it's like completely different from the mainstream patch. But it could detect like where there is an issue, and what is the definition of that more and better description of that possible vulnerability that can be really helpful. Another feature that we wanted our model to ideally have was like the ability to detect copied code from well-known sources that are not specifically secure, such as like a Stack Overflow that may have vulnerable code bases. So basically, the model could just mark it that this patch is coming from some insecure sources. And when we tried several code copied from Stack Overflow, we could see that the model could really not detect any pattern, any suspicious pattern. It could even we asked, breaking it down to basically finding a specific parts that are copied, but it gives a lot of description that this is a well-known pattern, for example, for capabilities to be used like that. And but at the end, it was like I can't really identify any specific evidence that says that this is a Stack Overflow code. So basically, for giving more information for adding more information to the model, we picked a lot of similar code from Stack Overflow on specific kernels areas that were related. For example, the crypto API. These are, for example, the files, the file IDs, like this number of files that are copied from different Stack Overflow responses, but they're all really tagged with that crypto API from the kernel. And then we use the assistant API. That's basically it's useful for feeding more information without also you have this model that's you don't need to repeat a lot of instructions for it again and again. And it can be useful for feeding a smaller number of sources that you want the model to be aware of. And so this was actually a very simple and naive way of feeding the model. As you can see, the RAG model that's basically described here, just as we did, feeding files, is really, you cannot really scale for more complex pattern. But even for this case, it was helpful that like at the end our assistant was like, yes, that code seems to have a specific patterns and it's copied from Stack Overflow. So for basically this kind of like pattern detection, we really need like a larger number of like data and more sophisticated ways of like fine-tuning our model. But even this small like improvement, a small set of like feeding the code spaces for the exact like related parts of the kernel from Stack Overflow, and using the Assistant API was helpful. So the result we were seeing from like the both previous techniques were not really like good results, and they involved a lot of still manual like interactions, and it was not really something that can be useful much in and or be reliable really in, to be used in kernel bug discovery. So the next step was that so can we basically really improve like the LLMs knowledge on some of the specific like criteria that we care about, like the vulnerabilities that we care about, and we want like only for those like things have a like proper like improvement on our LLM. And that's why the next step was using OpenAI fine-tuning API. And for that, basically, like not all like GPT models can be fine-tuned, so they have some of the models that you can fine-tune, and they suggest that GPT 3.5 Turbo is better for fine-tuning. So we tried that one, and it's also less expensive than GPT-4. So we were looking for some data that basically could help us for fine-tuning. And kernel CVs are actually not that helpful. So the only thing that I saw that they can be useful is ranking the severity of vulnerability. So they can say, okay, this attack is similar to this previous CV, so it can have this like a specific severity, like it's a high or low. But it wasn't really helpful because the descriptions are like not that detailed, so it wasn't really helpful with detection process. The other thing I was like curious about was basically, we have more complex forms of attacks that you can see, like we have a lot of good security blogs about them, and can we use those sources, like for example, Project Zero exploits on improving or LLMs or model understanding. And this is, for example, one of the examples that, so we picked several like Project Zero sources, change the format, fit them to basically have the same like fine-tuning format for OpenAI. And so basically before this process, our model couldn't really detect what's happening in that code base on RMAP. That was an issue on the anonymous virtual page areas. And after the process, they actually, surprisingly, the model could really pick what was wrong, describe like really in details that this is the problem, that like, for example, we have these mapped pages that are having a dangling page and pointer, and this causing that. And so I asked that, like, can you, now that you know the attack, can you write a patch for RMAP to fix that? And though it could describe like exactly where are the problems, it couldn't really fix that. So the patch is like really like not useful. It's really basic, but it could detect that this area, this anonymous VMA structure, shouldn't have this pointer, and the actual patch, like, it's not comparable. Like, the actual patch is very detailed and like not even comparable from accuracy to our model, but it could detect that these places should be changed. So that was an improvement, and it could identify that this like code can cause this complex attack that was described. Another source for like fine-tuning our models to know more advanced set of attacks are academic papers. They usually come with a lot of technical descriptions of that categories and also all the related works. And if they're like having open source data sets, actually that's also very useful. Like after you fine-tune the model, you can test that the model is really memorize all the details. And so, for example, in this case, we picked 3 papers that are coming with like open source tests, like the kernel code tests that they're used for their evaluations. And we could see that, like, for example, in this simple case, after the fine-tuning, the model could say exactly which lines are a problem, exactly where the type confusion is happening, and how this can cause like more complex attacks. That was kind of the high level and descriptions that described in the paper. So it was interesting result. Similarly, for another paper, we could that was more on like basically the memory leaks that you could reason with through the memory ownership. And again, we fine-tuned the model, and it could detect test cases that at the end we grabbed from the paper and their open source tests. And so these are not large number of papers, so the results are not that reliable. And basically, we were just trying to know what are the limitations and can be like helpful to with the model. So the results are interesting, but at the same time, there are like the number of tokens that, like, if you basically break the tokenize the papers, and those are like really a lot of tokens, and it can be really expensive to scale it in a large number of like papers. So it can be useful for a specific sets of vulnerabilities that like if you're looking for this specific, for example, memory vulnerabilities, but for scaling that, it needs more work, more advanced techniques for feeding these data. So another useful data source, specifically for low-level kernel development, like when you're dealing with hardware or hypervisor, the architecture docs and ARC manuals, like ARM manuals, like, as you know, these are very long documents and full of details that can be really helpful for finding like bugs and debugging. And so I started with a relatively small one because first it's very expensive to like feed that like large, probably millions of tokens. If, like, for example, it start with Intel manuals or something like that. So I started with a smaller one. It's about 200 pages for Hyper-V, and that has like images, tables. So one of the things that was useful was having 2 versions, like text-based tokenization, and then converting the PDF to a lot of images and extract them separately. And so this was basically helpful for finding like the fine-tuned model was actually really knowing better about details of like basically MSR configurations for Hyper-V and hypercalls, and it was like basically completely different in describing my like Hyper-V like related codes was looking at, for example, our VSM kernel module, and it could find 4 issues that they're not part of the mainstream yet. Like we didn't test on the analysis on mainstream. It was mostly on my dev environment, like on VSM codes that needs to be verified. But yeah, it was like really surprising that it could understand like specifically hypercalls and MSR configurations much better than the previous version. Our final like fine-tuned model could do like really much better on our small data set. So from our 32 mainstream patches, it could identify like 29 of them. Like the bug was identified exactly the bug that was expected from like the 15 kernel codes that like we asked for file function by function, like line by line investigation. It can find 11 security issues that these codes are internal. They're not part of the mainstream code, so they need more investigations before disclosure. And so this is a promising result. And of course, it cannot be generalized because our sample is very small. It needs like a lot of improvements, much better set of like complex data or better sets of like vulnerability description and like for example images, architecture, video descriptions, or like attack conferences that are specific on like for example Black Hat, or like specific on attacks and vulnerabilities, or audio descriptions of vulnerabilities. So these sources can all be combined together as a multimodal approach that I think it would be a very promising approach. And at the same time, if we go to that direction, we should also consider that there are a lot of security problems with LLMs as well. We should be aware of, like specifically if we're using formats like images and videos, they can be like poisoning attacks, injection attacks, and on LLM. So there are like other security considerations to consider for those kind of data. But still, I think it's like really promising for us to integrate LLMs for improving security of the kernel. So thank you for attending my talk, and please feel free to ask any question. I also want to thank like James Morris and Paul Moore for their help. They're providing like their feedback, their help with the brainstorming, finding patches, and that was very helpful. Thanks a lot.
Want to say anything?
Yeah, I think I said that.
They got it.
Okay, let's get started. Hello, everyone. It's so nice to see you here. My name is Corin. I'm currently a PhD student at UC Riverside under the guidance of the Professor Zhiyun Qian. So our group is actively researching on system security, especially for the Linux kernel. And my research mainly is focused on the kernel vulnerability and also the program analysis. So today I'm going to introduce our recent work, a hybrid alias analysis, and its application to the Linux kernel. So this is the agenda. So the first, I will introduce the problem that we are working on, and also I will then introduce some background around that. And finally, I will jump into the program analysis world. So the motivation is that we realize that many kernel access control mechanisms are rarely used because their rules are not easy to derive, or the derived rules are actually not sound because the analysis themselves are not sound. This might cause some runtime issue if you have some false negative in your analysis. So to address that at a high level, we proposed a novel alias analysis framework that makes a precise, scalable, and sound alias analysis on the whole Linux kernel become real. Even we can analyze with the all-ES-config Linux kernel, which turns on all possible modules, and is quite large for analysis. So we also made many efforts to specifically support many Linux kernel code features, such as typecasting and pointer arithmetic, which are not well handled before in previous work. And eventually, we have used our analysis to help derive access control rules for some existing kernel access control mechanisms, showing the promising results and some improvements. So for the background, so the kernel is always under exploitation, mostly because of some memory safety bugs, such as the use after free and out of bound, or generally speaking, the dangling pointers that point to the place that it should never point to. And the kernel will crash because of the memory safety bugs, but the exploitation will start from there. So one way to mitigate the kernel exploitation is to use the access control, which determines the access rights for a subject to an object, ideally following the principles of the least privilege. So we are all familiar with many high-level mechanisms, such as the user authentication or file operations, like the read-write execution, and some resource isolation mechanisms, like the namespace and the seccomp. But let's think about it at the low level, so the program level, from the memory safety perspective, or say the relationship between the pointers and their points to objects. So the most ideal access control here should follow the least memory safety privilege, which means a pointer should only access the permitted memory objects, or a pointer or a memory object should only be accessed by the permitted pointers. So no dangling pointers that should point to the objects that they should never point to in the source code. So to achieve that, in practice, there are many access control mechanisms or prototypes. For example, the read-only memory page maintains the object that should never be accessed through a write. For example, the constant variables, that once you define a constant variable, you should never change its value during the program execution. So, and many other mechanisms, we will introduce two of them real quick. So the first is the read-only after initialization, or say the RO after init. It's a memory page-based mechanism that is used for protecting the global variables. We know that after the kernel compilation, a constant global variable will be put into the read-only section, since they are statically defined and would never be changed dynamically. But there are some other global variables that will only be initialized during the kernel boot and the kernel initialization. So also it will never be changed afterwards. So the RORP init is proposed to make such variables read-only just right after the kernel initialization, because it will never be changed after the initialization. But the challenge is that it's hard to tell if a global variable will be changed or not. Given the complex nature of the Linux kernel, it's hard to see that where does this global variable, the address of it, for example, flows to. And it's also hard for developers to track the global variables and confirm all its changes only happens in the initialization stage. So after 6 years of this mechanism being proposed, about only 500 global variables are manually tagged by the developers. And there are also some global variables that are indeed could be changed after the kernel initialization. So for example, the mode pro path, which is a highly corrupted global variable in many recent kernel exploits. So we cannot put it into the read-only section even after the initialization, because it could be changed if we turn on the system control config. But the truth is that only few pointers in one single function of the system control module in the Linux kernel will modify it. And all of the exploits, for example, that using the IPC, using the LED filters, corrupted it through those dangling pointers in those unrelated modules. So in other words, that if we can identify all the legal pointers that point to the mode pro path, we can filter out the illegal pointers and protect it through some pointer level access control. So we realized that the key building block to derive the memory level access control rule is alias, or say the pointer analysis. So for example, that given a global variable, if we can find all its pointer aliases, like to say that all the pointers that might point to it, and check if they are all used as read-only after the initialization, then we can confirm it could be RO after init. And also for more fine-grained access control, like we discussed before, alias analysis will naturally derive the points to set of the pointers, and of course the pointer set of the object. But in past decades, we have so many great works on the alias analysis. So why do we need yet another alias analysis? Well, the quick answer is that there is no good enough solution yet, because all of them take different design trade-off, and none of them performs well for Linux kernel in the fundamental dimensions: soundness, precision, and scalability. So the soundness means that there should never be true alias is missed, and precision means less false aliases. And also it's very important to be scalable to the whole Linux kernel, which is quite large with reasonable precision. And also, generally speaking, all of these analyses can be divided into two categories: data flow-based and type-based. So first, let me introduce the data flow-based methods. Now we are jumping to the program analysis. So assume there is a pointer in the P1 in the Linux kernel. So it could be the address of a global variable, or say it point to the global variable initially. So to figure out the aliases of this global variable, we need to figure out where does P1 go to. So the data flow analysis is straightforward. It looks for the data flow of the P1, and eventually it figure out it flows to P2 and P3, or say the P2 and P3 may point to the global variable. Well, sometimes it's not that easy case. Actually, it will be much more complex in the Linux kernel. So the data flow might go through millions of nodes that across many global variables, heap objects, system calls, so on and so forth, make the situation much more complex and difficult. So intuitively, data flow analysis can only finish the analysis in a cannot finish the analysis in a reasonable time. So then we take a look at the type-based alias analysis. So the type-based methods are more straightforward, it doesn't trace the data flow. Instead, it looks for the type of the variable, for example, the defined type. For example, assume the P1 is a structure A pointer. So with type-based analysis, it will directly derive that P2 to P5 as the aliases, since they share the same type. But P4 and P5 are false positives here because there is no data flow between P1 to P4 or between P1 to P5. So you might think the result is reasonably good because it only introduces 2 false positives. But it could be much worse in practice. So assume the P1 is now an integer pointer. It means that millions of the integer pointers in the Linux kernel will be the aliases, which is definitely an unacceptable result. Well, there might be some type-based variants that try to refine the results based on some context. For example, here we find some context 1 and context 2 and to differentiate out some integer pointers. But those type analyses are based on the strong assumptions that are not always held in the Linux kernel, and things would be much worse due to the typecasting and some undefined language features, and the result is still not acceptable. So it's too imprecise to use the Linux kernel. So in a summary, that the data flow-based analysis are more precise. Data flow analysis and type analysis. So we will illustrate our idea with a simple example here. So still start from the P1. At the beginning, we are in data flow mode to trace the data flow. But instead of tracing the data flow all the way down, we look for a suitable time to change. So for example, at the node N1, which is a structure B pointer, with the insight from the type-based methods, just like taking a shortcut, we switch to type mode and teleport the data flow to other structure B pointer nodes and continue the data flow there. So it's worth noting that the data flow from P1 to N1 is not a trivially an integer pointer cast to a structure B pointer. It could be the case that P1 is actually an integer pointer field of the structure B. And correspondingly, those teleport terminals are also the same field of the structure B. For example, P2 is a structure field of the structure B N2. So at the high level, we do data flow analysis by default. Meanwhile, we look for a good chance to take the type-based shortcut. And then we continue the data flow analysis afterwards. And more interestingly, there is actually a more precise strategy. So this time we won't choose to take the shortcut at the N1. Instead, we keep tracking the data flow. When at the N4, which is a structure C pointer, we can choose to take the shortcut by the structure C and potentially get a more precise result. One of the precise reasons is because that structure C is less commonly used than structure B. So taking the shortcut of the structure C goes to less nodes, which just means that it's more precise, and we'll get a more precise results. So in the extreme case, that if we don't take any shortcut, the analysis will fall back to a purely data flow-based analysis. So it shows that UNIAS is not a simple alias analysis. It's actually an adjustable and unified framework that allows you to have different data flow and type strategies and achieve different trade-off in terms of the precision and the scalability. So in addition to that, UNIAS also provides customization for different variables, since it's a per variable analysis, meaning that you should always give an input variable to start your query or to start your search. That allows you to apply different strategies to different variables and tasks. So for example, that some variables may need a more precise result that require more data flow analysis, and you also have the freedom to do that. So let's go back to the insight. So we now know the key is the structure field, which we collapse the same structure type fields to be connected, and then we can teleport our data flow from one to others. Such a strategy is actually an over-approximation, since there might not be a true data flow between the same type field nodes. But we can still improve the precision given the adjustable framework. As we just discussed before, we can choose to take the shortcut through the less commonly used structure types to limit the search space. And also we can try more data flow, just to try more before taking the shortcut. So in the previous case, the precision is improved not only because we choose the less common type structure C, but also we do more data flow before the shortcuts. Such a data flow constraint requires a symmetric data flow after the shortcuts. So for example here, before the structure C, we have the data flow constraint as the P1 is stored to a structure B field, and such a structure B is from a structure C field. After the structure C shortcut, after the teleport, we also look for the same structure C to B field and also a loud instruction from the structure B field. So since we store something before, which is necessary to match a loud afterwards. So you could imagine there might be 3 instructions on the left, store instruction on the left, and correspondingly they requires 3 loud instructions on the right. So you always need to make the asymmetric balance. So in other words, even if we take a very common structures as the shortcut, when we choose to have more data flow constraint before, we can expect less matched data flow afterwards, which is still precise. And we try to handle some kernel specific code features. So the first is the typecast. So when dealing with types, we always need to handle the typecasting, especially in the Linux kernel, which has a bunch of the cast. For example, here in the source code that there is a typecast from structure A to structure B, in which case if we want to take the shortcut through the structure A, we need to also take care of the structure B because there is a typecast. Well, traditionally type-based methods handle it through a union find strategy. They will do a linear scan of all the typecast instructions in the whole kernel and consider the type that once cast to each other to collapse to the same type. Thus, it will, in this case, consider the use of the structure B as the use of structure A, and thus would derive P3, P4, and P5 are aliases of P1. However, in Unius, we have a more precise solution. We also scan all cast instructions, but instead of collecting the equivalence at the type level, we collect it at the object level, which means that we will only teleport to the exact pointer that experienced this cast instruction. So here is the A3 to B1. So the data flow analysis will only continue from the B1 and then derive P3 as the alias. And if there are indeed data flow between B1 to B2 or between the B1 to B3, the data flow analysis would also automatically trace it and handle it. But in this case, there are not. So it does need to do so, and the result is more precise and is exactly the ground truth. So there are many undefined code features used in the Linux kernel source code. So mostly the pointer arithmetic. Instead of assuming they are not existed, we chose to address them through some formal strategies. So for example, due to the typecasting, a structure object might be accessed through different type of pointers, even through some void star pointers. So in which case, if you want to match such field access, for example, match at the left and match at the right, we need to normalize them into the byte offset instead of the field indices, because different field indices in different types might access the same memory offset in the object. And we also relax the field arithmetic rules for the Linux kernel, because, for example, we allow the field arithmetic from the field to base, and even we allow the negative offset of the field access. So a typical case here is the container of, which essentially access the structure base from the field through a void star pointer arithmetic. So it's worth noting that unlike many previous works that try to handle the container of specifically, through some model. UniS naturally handles it through the formal handling of the pointer cast and the pointer arithmetic. So we didn't specifically handle it, but by handling these two code features, we automatically handle the container of. So the UniS could handle more pointer arithmetics or undefined behaviors in practice. And we design and implement our analysis based on the grammar of the context-free reachability framework, which solves the analysis as a graph reachability problem. So for example, if you give me a pointer that I can, through the graph reachability research on the graph, I can tell you the points to object of this pointer. Or if you give me a memory object node on the graph, I can search the pointers for you. So UniS seamlessly unifies the data flow and type alias analysis, and is sound by design. That's why also it's called the UniS, so unified the alias. So it also handles the multi-entry nature of the Linux kernel through the flow insensitive analysis, which means that different system call execution orders don't affect the data flow results. And our results is always conservatively approximated beyond the system call execution order. And as mentioned before, it's an on-demand per variable analysis. So you can choose different strategies for different variables to achieve different trade-off of the precision and the scalability. But there are still some limitations in the UniS. So for example, first, some undefined code behaviors rather than the pointer arithmetic that we mentioned before. Kernel developers even write the code in a way that cast a pointer to an integer and cast that back to a pointer somewhere else. So the reason is that they don't want to accidentally dereference the pointers during the propagation, or they try to do some pointer arithmetic through the integer arithmetic. But since the UniS work on the SVF, which is a static analysis framework based on LLM IR, so we only work on the SVF pointer assignment graph, which is a data flow graph provided by SVF, which would only represent the pointers, not the integers so far. Thus that cannot recognize such arithmetic and handle it. So it might be some future work. And there are many inline assembly code in the Linux kernel, which are not represented semantically in the LLM IR. So some potential solutions are trying to model the assembly code as some external APIs, or try to lift them to the LLM IR through some decompiling strategies. And also the on-demand analysis somehow limited the scalability of the UniS. So even though the UniS search in the search space of the UniS is the whole kernel code space, but it's not like a whole program analysis, which will analyze the whole program at first and query for the results afterwards. Instead, the UniS needs to query first and start the analysis on demand. So start the graph search after you query the things. Thus, if you query more variables, it will be more time consuming because you need to spend more time. But it's fully parallelizable, so if you have enough CPU cores and threads that you can get a good scalability. So we evaluated our analysis on some applications. For example, the ROR init mechanism that we mentioned before. So as a result, UniS can analyze all 12,000 global variables in the Linux kernel version 5.14 with the default configuration in 1 hour time budget. So where the Anderson-based data flow analysis can only analyze about 3,000, so 1/4 of the UniS, and showing the UniS is more scalable than the data flow-based methods. Also, compared to the type-based methods, UniS can protect 6 times more global variables by identifying them as R of init, because type-based are too over-approximation to use, meaning that the UniS is more precise than the type-based methods. So as a result, that UniS find about 10 times of the protectable global variables than previous human efforts So we tested the results by a 2 weeks fuzzing and confirm only few false negatives are introduced due to the limitation that we discussed before, the inline assembly code or the point to integer. So thus there are still some improvement space here, and we are also researching on some strategies to decrease the false negatives in practice. But the design itself is still sound. So we do need to handle some implementation level details. And we also tested about the tunability of the UNIS. So by setting the different shortcut strategy, for example, taking the shortcut more aggressively, we do improve the scalability of the UNIS, but also sacrifice the precision a little bit. And go back to the highly exploited global variable, the multiple path. Well, the ground truth is that it will have 3 pointer aliases in one C code file, and the UNIS find 19 pointers in 6 C files, which slightly over approximates the truth. But no matter what is good enough for preventing all related exploits. As a comparison, that data flow-based methods find 11 pointers in 4 C files, while the type-based methods find millions of the pointers, because the multiple path global variable is actually a character array global variable, which is essentially a void star pointer in the LLM-IR. So we also apply the UNIS to protect the global variable with 2 mechanisms, our offering init and the general software fault isolation. So to our best knowledge, in the recent 6 years, there are about 13 out of the 37, so 1/3 of the open exploits once leverage the global variables. And as a result, the UNIS derived that all of those exploits are using illegal pointers. So if we apply the access control mechanism through the rules derived by UNIS, we can prevent them all. And there are also many other potential applications for the UNIS. So for example, to derive the rules for the access control mechanisms, such as the pointer authentication and write integrity, which still need some derive of the access control rule automatically. Also for the general program analysis, given that the alias analysis, or say the pointer analysis, is actually a very basic building block of almost all program analysis, such as the taint analysis and maybe some bug finding analysis, because UNIS is much more precise. So even if you are, and even if you are not, even if you are not doing anything around the program analysis, you might still benefit from UNIS. You can still try it when you're writing the code for the Linux kernel, because you might wonder the potential points to set given a pointer or find the pointers given an object in the Linux kernel source code. So feel free to try it. So it should be a tool that helps you to figure out the pointer and the object relationship. So to summarize in this work, we propose a novel alias analysis framework that principally unifies the data flow-based and type-based methods. It is sound by design and can adjust the precision and scalability and can apply to different variables and tasks on your demand. We apply the UNIS to analyze the use of global variables. So then we prevent all the global variable related exploits in recent 6 years with the suitable mechanism, access controls. So eventually that we find the UNIS in the solution space. That's it for my presentation. Thanks everyone for your time. Any questions?
At Google, we find that static analyses are best understood at code review time. And for that to work, you need it to be pretty stable under change. Have you seen if analyzing the kernel at different points in its history provide a fairly consistent view of the same variables that have existed in previous versions?
Oh, you mean can we support the incremental analysis somehow?
No, I'm talking about how flexible under refactorings the analysis is, because whenever you're tuning a static analysis, it can be very finicky, and that finickiness, just because you added extra curly braces or not, can make it unsuitable for including in the software development lifecycle.
Okay, so one thing that I want to mention that we also tried our static analysis always on the most recent Linux kernels. So it should be suitable for if the Linux kernel get update. And also the framework itself is written in a very brief way so that developers can easily add or delete any logic that on the framework. And the framework itself is basically a depth-first search. You could think about it like that. So that is quite easy and friendly for developers to work on that.
Go ahead.
You said you found 5,000 instances where we can mark read-only after init. Are we expecting some patches as output from this?
Yeah, this is a really good question. But indeed, that the one truth is that if you can check our paper, we mentioned that we find 5,000, but there are still 23 false negatives, and all of them because of the inline assembly code and also the pointer integer. And since the ROF init, if you really mark them as the read-only, is quite dangerous because after the initialization, if some variable is read-only and some legitimate code access it, it just crash the kernel. So we would like to suggest that developers could use our results and double check for that. That could be a better strategy. But since there are many implementation level dirty things that actually for the static analysis for the kernel, so it's not that safe to do so.
Okay. Is that list easily accessible? A list of 5,000 places that maybe we could use?
You mean if the result is acceptable, the false negative
like, is the list published somewhere that someone could actually sit down and look at each of those and say, yeah,
oh yeah, we are going to release that.
Okay, great. Yeah. I'm looking forward to it.
Yeah, thanks. Thank you so much.
I have another question. You have a claim of soundness. In order for you to prove a mathematical property about a programming language, you need the semantics as a mathematical object. Which one are you using for C?
You mean the semantic provement of the soundness, or?
In order to be a sound analysis, that's a mathematical statement over mathematical objects. And for here, you have a semantics of a programming language, perhaps C. Where is that model? What model did you base this off?
So the things that actually for the most of the C language features that, or say that all of the C language feature, if you indeed follow the code feature or the behavior, that we should already handle that. But the only exception is those undefined code feature, like you do some force arithmetic on the pointers or on the integers and turn it into a pointer, which is quite complex for the pointer analysis. And it's still an open problem for general program analysis, because the soundness is always based on some assumption, or just like you said, some semantic or some model. And we can confirm that under most of the code features we handled them, but there are indeed few implementation level things that are really tough.
So your model you've built from the ground up, or you're taking it from somewhere else? For example, CompCert has an entire big step semantics specified in Cook for C. And that is the kind of model that I'm talking about as a mathematical object.
Okay, that sounds some specific thing that I am not very familiar with. And we can discuss maybe offline about that.
Thank you.
Thank you. Okay, that's pretty much it for the presentation. Thank you, everyone.
Hello? Hello, everybody. It's exactly 2:50 p.m., and that means it's my session now. My name is Petr Tesarik. I have been around the Linux community since the early 2000s, on and off, spent time on crash dump analysis and various other smaller things. And lately, I have been working on this thing called Sandbox mode. This is a catchy name, and it attracts some attention. Thank you. Like upfront, I know that sandbox is a loaded term, and this thing has nothing to do with sandboxing, like namespaces and containers, whatever. It's a completely new thing that I tried out to protect the kernel from itself. And this is original research funded by Huawei Technologies. Thank you very much. I was contracted as an external consultant, so I'm not here as a Huawei employee. I'm just, but it was paid by Huawei, so yes, they deserve the credits. And let's go to the matter. Okay, so I'm saying sandbox mode is a new mode, like a new process mode. Until now, we had user mode, kernel mode, and I'm proposing sandbox mode. Why? If you look at the project goals, it starts with the premise that all software contains bug. Like, everything is buggy, it's just a matter of how much buggy it is. And the goal is to improve self-protection by reducing the attack surface. I'll get to that. I mean, the problem with kernel mode is if there is a memory safety bug, then the whole system might be compromised, and usually is. And I also I had a second goal. Okay, if we make a sandbox mode, or if we reduce the attack surface, can we do that so that we can run kernel workload without interference from less privileged entities? Means like if for example, if your kernel runs with the lockdown LSM, then it means UID 0 is not as privileged as the kernel. And that means if the kernel is locked down, then user space or user mode is not an option. Okay. I'll start with a very high-level overview. Excuse my drawings, I'm not an artist, but it should illustrate the point. Let me first explain where we stand today. So the options if you want to run something as a kernel workload is, well, obviously run it in kernel mode. The problem with that is, okay, these barrels are like gunpowder, and if you allow something that is buggy into this storage and it contains a bug, well, you can imagine what happens. So that's generally not a good idea, and although the Linux kernel is doing that, with a growing code base, might not be sustainable. And sometimes it's not even a good idea. Like sometimes you can't really completely audit the code that you need to run. So this is suboptimal. Like this is the full attack surface. We have alternatives. we could make an eBPF program. That's better. It has some limitations. I'm showing here, the main thing is it's no longer really kernel mode. It's eBPF code that gets translated, like I'm 3D printed on my illustration. And this also has some limitations, like the size of the 3D printer means the size of the eBPF program. And most importantly, there's this verifier. We only can run it in the kernel because some code has verified that it is safe to run. And this verifier is quite complex, and it also limits what can and can't be run. Like eBPF itself is Turing complete, so it can run anything, but the verifier will not anything run. So, okay, maybe it's good, but it has some limitations. Also, currently eBPF programs are loaded from user space, so that's not an option if you really can't afford to allow interference from less privileged entities. That could be fixed. Okay, so I'm just mentioning it. That's a limitation of the current implementation. The other points are like inherent to the solution. Okay, so if we don't run an eBPF program, well, can't we use user mode? Really, like there's this user mode driver, and this user mode driver is in its own space that is separate from kernel mode. There's some communication path, and yeah, that way, if there is a bug in the user mode driver, it does not have any adverse effects on the rest of the kernel. Well, there are some, okay, this did not work well. So these are attacks on the UMD. One of them is ptrace, the other one is kill, so signals and so on. User mode driver is protected. The communication path is also in danger, like it's possible to find a file descriptor through procfs, for example. It is also possible to like change the scheduling priority of the user mode driver, and if there is anything in the kernel that needs to run before or after or whatever. So these are attacks, and most of them are like, they are currently mitigated. It's just that user mode was not designed to run kernel workload, so there is fear if you rely on user mode being fully protected, then that may not play well in the future because someone adds a new feature to the kernel like IOU ring and forget that, okay, we also have to make protections for UMD. So yeah, it kind of works, but may become a whack-a-mole game. So how do what do I suggest? I'm proposing something that's called Sandbox mode. So you can see this is very much like the kernel mode, but there is a wall. There's a wall between code that runs in the sandbox and the rest of the kernel, which means it's exactly as dangerous, but if the sandbox blows up, the rest of the kernel can continue. That's the basic idea. Now, you may ask, yeah, this is good, but if it is isolated, what can you do with a sandbox? Right, so this is, okay, sorry, this is contain damage. Right, right now I'm not protecting sensitivity, so kernel data is read-only. So if sandbox mode needs something from the kernel, it can simply dereference a pointer. Kernel code is mapped into the sandbox. Might not be a good idea, I'll get to that, but yeah, by default it is. And some things can be called directly, so if you don't have any dependencies on pages that are not writable from the sandbox, which are behind the wall, so to say, then yeah, you can just call it directly. If you need to modify something that is behind the wall, well, that will fail. And for example, kmalloc will fail. That's a big limitation. It is also possible to share some data with the sandbox, like there's this shared page on the top of the wall. So that's something that the kernel can write into and sandbox code can write into. If you do that, keep in mind that it is a potential, like it is a hole in the isolation, so to say, which might be acceptable sometimes, might not be acceptable other times. We'll get to that. The thing is, if writing fails, then it is possible to intercept this, and depending on the isolation strength and policy, either fix it up or abort. So first I'll get to the isolation strength. The way I designed it, there is weak isolation and strong isolation. Weak isolation really does not do much. It provides the APIs, and it uses the guard pages that are implicitly provided by vmalloc, and copies data into the sandbox and out of the sandbox. So the thing is, if I go back to this slide, the sandbox starts with some data already. That, like these two barrels, and these were copied into the sandbox before it was started. And when the sandbox terminates, the kernel mode can copy out some data. So that's how it communicates. Weak isolation does not provide much. There is also strong isolation. That's the main goal. And that will switch to its own address space while sandbox mode is running. That requires changes in some arch-dependent, like in the interrupt handlers and in possibly other code to make sure that it works. That was rejected, by the way. So, but at least I wrote that for the x86 architecture, and that was rejected by the architecture maintainers. We'll see if the idea has some merit. I may try with a different architecture. So let me just quickly present how sandbox mode works internally, now that we know what it should achieve. I'll start with slide. That's how process modes work today. We have user mode, we have kernel mode. User mode can use syscall APIs. It is unprivileged. The kernel mode is privileged, and internally there are kernel APIs. These are not really well documented, at least some of them are not. Kernel APIs means function calls inside the kernel. How does this change with sandbox mode? Okay, so we still have this user mode, kernel mode, but we also have the sandbox mode. The sandbox mode is isolated, and it uses kernel APIs, which means theoretically you can have sandbox mode for each process in the system. It's like a new mode. That's why I'm saying that's a new mode. The essential features, if sandbox mode is isolated, how does it differ from user mode? Because user mode is also isolated, can't write into the kernel data. The big difference is sandbox mode is nested inside kernel mode. So if you look at user mode will just call into kernel, and the kernel will lazily do as little as needed and return. Sandbox mode is started from kernel mode. Externally, it looks like it is still executing in kernel mode. Like if you make a process listing or for profiling, tracing, whatever, it looks like kernel mode is just internally executing something else on the CPU. It can access kernel data. I said that kernel data can be accessed, and it prevents buffer overflows with byte granularity because we are copying in, copying out. So we're copying only as much as the trusted kernel mode said the buffer size should be. Violations are detected with page granularity because it uses page tables to achieve the isolation. Just to make, I'm listing the APIs just to give an idea how that looks in code. Each such sandbox mode has an instance variable. You initialize that, then you define the input and output buffers with SBM copy in, copy out, or copy in out if that's data that is copied in and then modified and then copied out. You can also share it with map read only or map writable. So these are the shared pages. And then you call the function and then you clean up. So that is easy. To make a function callable in sandbox mode, there's a macro which will just wrap around the target function. It will provide a call helper and a function which makes sure that the parameters are passed correctly. And you just then call it SBM call with the parameters. This is an example that was posted on the mailing list, which converted AA unpack, the UpArmor unpack function, to run in a sandbox. So you can see that it has this. It has some changes outside the target function, but no changes were necessary to the AA unpack itself. You just call it with SBM call. That's the last line before the commentary. Like there's this SBM destroy at the very bottom, then there's a comment line, and then there's this error equals SBM call. So I'm only changing how AA unpack is called. I'm not changing AA unpack itself. We still have a bit of time, so I'll spend a bit more time on the strong isolation. So now you have an idea how that looks in source code. What happens on the CPU level, in a strongly isolated address space, we are making most of the kernel address space non-writable. And only the buffers that are dedicated to sandbox mode are writable. That's why it is, and this is subject to the contain damage that I mentioned earlier. And there is no user space. I think there was a misconception about this. I'm not, if I run that like this, then the protection against accessing user space is lost. That's not true because user space is not even mapped in this address space. Now, that is good. What I had to take care of is interrupt handling. So I'm making a difference between intercepted interrupts and not intercepted. So not intercepted is where sandbox mode only wants to run the interrupt handler but does not really care what it does, like external interrupts from devices and so on. So the thing is, when such an external interrupt comes in, the CPU must leave the sandbox and run the interrupt handler in kernel mode, because obviously the interrupt handler was not designed to run in this sandbox. And then switch back. That's easy. And then we also have these intercepted interrupts. These are processor faults, and these may have to be handled. So they start the same, they enter kernel mode, and then they check policy if this kind of fault is expected, and in that case, it will fix up the fault. But if it's unexpected, it will abort. So what I mean with a fix-up, what is a fix-up? Okay, since sandbox mode is isolated and not privileged, it runs with CPL3 in my implementation. That's not a prerequisite, but it has some merits. I can get to that if people are interested. But because of that, it can't do a lot of things that kernel code normally does. For example, it can't allocate dynamic memory. But this code is expected to contain calls to such privileged code, like kmalloc. And the thing is, if this code does call kmalloc, for example, then this is, and the police says, well, yes, we want the sandbox to allocate dynamic memory, then the interrupt handler will switch to kernel mode and see, okay, we are expecting this kind of fault, and we can allocate this memory on behalf of the sandbox. So in some way, this is related to eBPF helpers, but is different because, like eBPF helpers, that's what eBPF programs have instead of syscalls, kind of. Yeah. Here we are trying to run native kernel code which contains like a call instruction, like a real CPU call instruction, and we'll just execute whatever is needed. I also call it a fix-up because it does not just call kmalloc. It also makes sure that the newly allocated memory is mapped into the sandbox, so sandbox can use it now. It may also check that it is a sane, like it may do parameter sanitization that would probably be needed for k-free, so that if there is a bug, you can't free a buffer that was not allocated in the sandbox. All this is theoretical, that has not been implemented. But the idea is, yes, a fix-up should do some sort of sanitization. And the sanitization might be actually shared with these eBPF helpers, possibly. Okay. So that's it. Essentially, I think this is the main core idea behind sandbox mode. And I want to give you some time for questions.
So how expensive is the setup and teardown of the sandboxes?
How
expensive? Like
okay.
Setting up the memory mapping, everything, how expensive is it to set one up and tear it down?
So setting it up may not be that expensive. Obviously, we have to allocate all the page table hierarchies. Entering and exiting the sandbox is kind of like, it can be expensive because obviously you have to make sure that the new mappings become active. Luckily, and that's why I said I run it with CPL3 on x86, because that allows lazy TLB invalidation. But obviously, it's not the full story. If there's any user space, well, the user space translations in the TLB are flushed when you start the sandbox.
Right.
So that is expensive.
What use cases you had in mind when you wrote this code?
Okay, the trigger probably is not the main use case I had in mind. Okay, there are a few. So first is if you have to run a binary-only module for any reason and you don't want to trust it, maybe you want to run it in a kind of sandbox. And I know that binary-only modules are evil and you should not be using them, but still there are people who have to use them. And second is, for things that do not run on process context, this TLB flush is not so expensive because we are only flushing a few pages that are actually used by the sandbox. And so things that make a complex thing like parsing user supply data that might be crafted to trigger a bug could easily run in sandbox mode. So this does not happen too often, like unpacking the up armor profile while usually you only do that once. Yeah, so things like that, parsing of user supply data.
So you're trying to act as a safety net between untrusted user mode and...
That's it. Make it harder to exploit an existing bug.
Yeah, thank you.
Hi, nice talk. So can this be implemented for ARM64 as well? And we use the same levels like EL2, EL3?
Yes, it can be implemented for any architecture that has paging, so anything that has an MMU. I haven't really implemented an ARM64 version, but I had some, okay, so that's in the backup slides. So if you had a sandbox mode on ARM64, you would run it at EL0. Because otherwise EL1, if you ran it as EL1, you would have access to privileged registers, so you could escape the sandbox. And the idea was like load a new value into TTBR1 EL1 and like when starting the sandbox, and then at interrupt entry and exit. Like implement something like KPTI for the sandbox. There are some, okay, I wrote down a note about config onmap kernel at EL1. Yeah, that's the KPTI for ARM. There are some TLB considerations, again, like we would have to allocate an ACID for each sandbox instance. And yeah, global entries. Yeah, we can also implement the lazy TLB flushing here. And there is also, it needs its own interrupt stack. It also needs it on x86. I skipped it for this presentation because that's an implementation detail. You can read it in the submitted patch series, but we would need something like that. There was a trick on x86 to recognize user mode from sandbox mode, which used the saved CS registers. We don't have that on ARM, so we would probably use a per CPU variable. But essentially, it can be done.
But this sounds a bit more expensive in terms of CPUs. I mean, imagine going from user space, and then coming to the kernel space, you do the context switching. And then from kernel space, you have to go to the user, the SBM mode, more context switching. So have you done any profiling? And then, like, is there any like, what's the possible impact in performance?
I definitely didn't do any profiling on ARM because I didn't even write the code. I just made a sketch how that code should look like. On x86, I didn't. Loading on x86, loading a new value into CR3 is a relatively expensive operation. But yeah, like it's manageable. On a 3 gigahertz CPU, the latency added by like entering and exiting the sandbox mode was under 1 millisecond, which is like, still a lot. Like if you're talking about nanosecond latencies, then this was noticeable. Would divide that by 2, but like, was on the order of like hundreds of nanoseconds, even if I optimize it.
It's still expensive, and
yes,
you usually go from user space to kernel for like memory allocations and on those things, and there'll be frequent calls to the kernel, and then you're switching again to the SBM mode. I think which will be more frequent. It's going to be more expensive.
Right. That's why I'm saying my target was things that do not run frequently. I wonder if the performance hit could be justified for some use scenarios. It depends a lot on like I said, it depends a lot on some factors that are unknown, like is there a user space that needs to be repopulated into the TLB, for example?
Exactly.
Just in that case, it's prohibitively expensive, but if there is no user space, then it might work.
Okay. All right. Thanks.
You're welcome.
The kernel text has commands in it that require CPL 0. So what does failure look like? I mean, you're going to get general protection faults, and does it blame the sandbox and make it easy?
Okay, so depending on what you want to have. So generally, yes, if it raises a general production fault, it will abort the sandbox and return an E fault to the caller. But if you so wish, you can write a fix-up for the general production fault. Like you may allow to disable interrupts, for example. But keep in mind, well, then the sandbox is allowed to DOS the CPU that it's running on. Okay? Any other questions? Then thank you. And that's it.
So this mic, yep, okay. Oh, did I miss the ice cream? No ice cream? Good. Yeah, I say ice cream and the room just empties. All right, so it's 15:50. I'm going to kick this off. So my name is Bill Roberts. I'm going to talk about System D, its integration with TPM 2.0, and some of the fallacies and pitfalls that kind of pop up when you're doing that type of integration work. So we'll get going. So with this crowd, probably a lot of people here have some background. Like I noticed a lot of the discussion or the presentations mentioned TPM somehow. But I'll just do a really brief intro to it. So if I say TPM, I mean TPM 2.0. There is an older 1.x device that kind of started the whole TPM thing. It's kind of really old. It's deprecated. I haven't seen one in a while. They're still out there, but yeah, we're talking about TPM 2.0. And so the TPM is this thing called a Trusted Platform Module, and it's a standard by the Trusted Computing Group. And at a high level, it provides storage, so you can say, hey, TPM, create me a key and store it through some protection mechanism. It does measurement, so we've seen a lot of talk about those PCRs. That's that measurement state that the TPM can provide. Reporting, there's a whole attestation protocol around the TPM. So it happens to do with signing the PCR measurements, how do you get them to a remote server and perform the attestation protocol. And then cryptography, so not only can it create keys, it can also use the keys to do things like asymmetric and symmetric cryptography, like RSA, HMAX, etc. AES, but not all TPMs support AES. This talk is mostly going to be around storage, the protection of those storage keys, and specifically the disk encryption key. So if anybody's familiar with Windows BitLocker or something like that, it uses the TPM to store the disk encryption key and protect it. And then that disk encryption key is eventually released later. And then so what is System D? So this is the init process, replaced the init system. It bootstraps most Linux distros, at least the ones I use. It provides a lot of stuff. It's not just an init system, it's an ecosystem of things. And one of the things that it has is native LUX disk mounting and TPM2 disk enrollment. So it has sets of utilities and things that are integrated into System D that let you say, hey, I want to take this hard disk and I want to enroll it with a TPM key for protection. So this is not a talk on System D versus init, and this is not a talk to be critical of System D. I know Leonard very well, and other projects have made the same mistake you're going to see along here, like Parsec. There's a couple others. So I want to talk about what these problems are and what we can do. And again, this talk is specifically, as far as System D, is going to talk about that LUX disk enrollment. So what is the problem? So there is a potential attack vector with TPM 2.0. So by default, whenever you send a command to the TPM and you get a response back, that is all over plain text. And so there's certain TPMs are going to be discrete, i.e. it's like its own little chip hanging out somewhere, or it's going to be built into the CPU firmware. And so the typical attack vector is like the bus. If you have a discrete TPM, you could hook up some wires on the bus and you could sniff all the traffic going to and from the TPM. But it could be other potential parts of the system. And I think a lot of the other talks about this in this conference have brought up different execution levels or different execution environments and usages of TPMs, whether virtual TPMs, however you're getting those bytes to and from a TPM, whether it's virtual or physical, and those bytes cross your trust boundary, you probably want to protect them. So this is a known attack, and the TPM 2.0 architectural docs actually describe this in detail. And then if you're actually looking for like a real world instrumentation of how you could perform these types of attacks, if you just Google TPM Genie, there's a great GitHub page. It's got source code. It tells you how to do it. It walks you through it. It's actually kind of fun to do. So while this is a known problem, that architectural documentation also describes how to circumvent it or to prevent it, mitigations. So there's these things called sessions. Unfortunately, to get the sessions, you have to opt into them. There's a lot of different sessions. If you look at the TPM documentation, which is very terse at times, the sessions you care about are these things called HMAC sessions. And you go, oh, well, HMAC's great, but yeah, it's like integrity, right? Well, there's other bits you can set when you create the session. There's bits for encrypting the data to the TPM, and then bits for telling the TPM to encrypt the response data. So you want to enable those types of bits. And you can think of this conceptually the same as TLS. And you want to do the same things that you would do in like a TLS session. Again, the attack vector is typically the bus, but again, like a point that I really want to drive home is anytime your bytes of communication leave the trust boundary, think about it. A lot of people just go, oh, I'm using the TPM, it's good. Well, maybe not, depending on the scenario. And another nice thing is when you enable sessions, whatever client application your software is that's communicating with the TPM, it's endpoint to endpoint, right? So no matter where that application moves, like if it gets moved, you know, ported to a different system, it still should work. So this attack has gotten a lot more press than I think it actually deserves because it was known. Here's just one, but if you Google the attack, you'll see like all sorts of documentation, or not documentation, but news articles. BitLocker's broken. You know, pick a vendor that's making a TPM chip. Oh, their security doesn't work. Typically happens to be around the firmware-based TPMs that are built into manufacturers' processors. So again, this could be thwarted with that encryption. And the problem that I'm going to show you is that people were even using sessions and thinking that they were getting these protections, but they were just saying, hey, TPM, create me a key pair. Now encrypt that communication channel with the key pair you just created. That kind of, you know, in a TLS session, you're going to walk that certificate back from the public key to actually make sure it's signed by some CA that you trust. You don't ask the server to say, hey, server, create me a key pair and send me the public key and I'll trust it. And that's kind of another problem that was around here. So the systemd support, so they added this support in. So systemd actually added that support for like a BitLocker type thing. And they added support for encrypting and decrypting hard drive contents. The way that it works in the TPM is that when you want to create one of these disk encryption keys for your hard drive, is you generate the disk encryption key, not the TPM. So there's two types, essentially two types of like keys in the TPM. One where you say, hey, TPM, create me the key. And one where you say, hey, TPM, here's the key. Disk encryption keys are, hey, TPM, here's the key, I'm going to give it to you. And you might ask, like, why? Why not just let the TPM handle all of this? TPM is slow. TPM is not good for bulk encryption. In fact, most TPMs do not support like AES or something like that. You actually want to get that key back in raw bytes because you can hand it off to certain types of hardware, disk controllers, where you can actually, they'll perform the encryption and decryption, so it's not even done in software. So if you want like that hardware acceleration stuff, they kind of need the key to do the work. So because this key is essentially going to and from the TPM, and the TPM is really just kind of providing data at rest protection for the key, that man-in-the-middle attack is kind of useful because you can get that disk encryption key. So here's the timeline of changes. So these are systemd version numbers on the left. Version 248 is where they had that initial TPM 2.0 support with no attempts to do any type of encryption. Then they enabled session support. And then that's kind of when I went to go look at their implementation and noticed there was a problem. And then I kind of worked on mitigation steps after that through version 252 through version 254. I forget what version they're on now, but it's like upper 250s, might even be 260s by now. I don't know. They do move pretty quick, but most of the recent distributions, like I'm on Fedora 39, it's new enough where you're fine. So visually, this is what I've been explaining. If you're just in a plain text scenario, you have the key, it's coming from the TPM. An attacker on the bus or on whatever communication channel it is gets the key, they have your disk encryption key, they can use that in an offline attack. Yeah, not particularly interesting, unless you're the attacker. Version 251, so this is where systemd actually was like, hey, let's fix this and actually solve this problem. So they enabled the session protections. Again, it's just like TLS. But the weakness here is that they failed to verify the public key. And this is like the second time in a public repository I've seen this happen, and I'm sure it's elsewhere, and I just don't know about it. I've seen it in a lot of proprietary software. So when you're using the TPM, verify your public keys. If you're using them for, you should, verify your public keys. That's a good idea. So this would be akin to like trusting the any root CA for TLS or accepting any key pair over SSH. Like you're just like, oh sure, that's a fine key, it's good enough. And so how would the attacker though actually do this, right? Oh, actually, let me show you. So this is their vulnerable code snippet. This is generally the code flows I see in other people's software. They'll be like, they'll call make primary. They'll get a key pair from the TPM. And then they'll do something like, all right, I'm going to start up that encrypted session. So if you're auditing code bases or you're working around the TPM stuff, keep an eye out for stuff like this. And then make sure that, like something like make primary or make encryption session is actually verifying the public key. And one thing to note here is the way that the TPM works internally is the keys are in a hierarchy. The primary key will be the root key within the key hierarchy, and then you can make child keys under it. So that's what that means. Like if you see primary key, it just means it's like the root parent key for a key hierarchy. Okay. So this is where they added the session encryption. So how would an attacker actually take advantage of this? So an attacker would say, all right, you want a key pair for the session encryption. So like when they call make primary, as the attacker, I just give them a malicious primary key back where I control the private key. And then I just, as the attacker on the bus, I just perform what the TPM would do, which is session encryption. I do all that. If I need to forward commands to the actual TPM, I can. I'm in full control. I can decrypt the communication stream. I can send stuff. I can see all the data coming back. And they have no idea. They would never know. So in this case, when they send the key encryption key back, or the disk encryption key back, you just decrypt the communication stream and you have the key. And the client application, in this case systemd, would never know. So that's when I saw this, and I was like, okay, so what can I do really, really quickly to make this a little bit harder to pull off while I figure out how to fix their code, and also figure out if they want patches. So the simplest step was to add something called a bind key. So in the TPM, when you set up a session to enable the encryption between the client and the TPM, there's essentially two ways you can set this up. One's called the TPM key, and one's called the bind key. In the TPM key, you use the asymmetric key pair to encrypt a salt with the public key, and then you send that when you start the encrypted session with the TPM. TPM has the private key. It can decrypt the salt. That salt is used to seed the session key. The bind key is, suppose I make an object in the TPM and I put a password on it. That password is known by me on the client side because I created it, and it's known by the TPM because the TPM has to actually perform checks against that password. And what it does is you can use the bind key to establish the session key because that's the shared secret between each side. So instead of actually having to encrypt something and send a salt over, you just use the password as a symmetric secret to enable everything. The problem with this, though, is that any recorded traffic can actually be decrypted offline. So you could use a crack attack on it, dictionary attack or something to derive the password and then decrypt the traffic. So like weak pins, so like if you've used this feature on systemd, it's like put in a pin. Most people are going to be like 1, 2, 3, 4, so it's not really useful. I'm going to skip the rest of that. So version 252, this has the bind key. So we set that up. The attacker in this case could still be sitting there and faking the encryption for the primary key, but they couldn't do the other half with the bind key. So they could get the traffic back and they would see the layer of encryption from the bind key, but they wouldn't actually be able to do anything useful. They'd have to take that information and then take it offline and try to crack it. So how can we make that better? So it was a quick stopgap because it was literally like a 2-line change. It took like 2 seconds. They accepted it immediately and put a release out. But again, the traffic can be brute forced. So how do we fix weak pins? We add entropy to weak pins using a PBKDF. So we used HMAC SHA-256 because they already had HMAC and SHA-256 there in their crypto library, so I just had to put them together in a PBKDF. The other nice part about this is, so we have to store the salt. That gets stored in the LUX metadata for the superblock. But now, like, if you have your disk encryption key and it's protected by pin 1, 2, 3, 4, well, anybody could go offline around that, go straight to the TPM and be like, oh, give me the key. I know the password. It's 1, 2, 3, 4. Now you need to have the salt to do that. So that greatly also protects users like weak pins from just having another backdoor into the TPM. And this really just leaves kind of like one more task left. And so here's kind of like a visual of what I was just describing is it's the same thing as before, but they can't really take that offline now and mount that attack. It'd be much more difficult. Yeah, see, the attacker's sad. So the last thing, and this is like the thing that I really want people to be looking for if they're working on TPM, is like if you're going to start an encrypted session with an asymmetric key pair, do this. So this is the TPM key parameter in TPM2 start auth session if you're actually looking at the documentation. I'm the maintainer of the TPM2 TSS project on GitHub, so we have something called an enhanced system API that makes this process easier if you use the native ESYS-TR types, which some people do not like. But the idea here was to bind the object's location in the TPM. So TPMs just have handles to objects with the name of the object, which is the cryptographically unforgeable actual object. So like attackers, you need the name and the object location to guarantee that you're talking to the right thing in the TPM. So if you use ESYS-TRs with the Enhanced System API and you use that to start sessions, you're just fine. If you use the Feature API, which is probably not going to be useful for most of this audience, it's definitely more of like a high-level API. But if you're in user space, systems level programming up there, that'll be fine. And the Feature API does this all under the hood for you. You just call functions like, give me the key, and you don't even have to worry about it. The ESYS-TR gets stored in the LUX metadata. So where we stored that salt in the super block, this just gets shoved in there as well. And the security model around this is first to set. So when you enroll the disk encryption key during that time, when you seal it to the TPM, that's when we actually record what the primary key should be for the encrypted session. So this is like SSH when you're like logging in and you accept the remote server's public key fingerprint. So again, eSAPI will take care of everything. And this prevents the attacker from supplying that public portion of the key. Because instead of getting it from the TPM, you're just getting it from the super block for the disk. And then all the unsealed traffic within systemd is protected by sessions now, even when no pin is present. So like the bind key approach only works if the user specifies a pin, but if they do a pinless setup, now they have those protections as well. And this allows different auth sessions, different like models of protections for the keys. So like Leonard was just pushing patches up to systemd yesterday where you can do like PCR policies and other things. So, and have all those encryptions and protections in place. So in this case, this is just not even possible, and the attacker is sad. So if you're on version 254 or greater, everything should work and be secure. There was kind of some miscellaneous issues that I fixed along the way. Systemd was creating a primary key and every seal and unseal, which is really, really slow. Even though they were using ECC, which is way faster than RSA, you don't really need to do this. And there was actually no way to specify the owner hierarchy, the owner auth for the hierarchy that the primary key was made in. So which means if you actually deployed a TPM with an owner password set, which is you should, it's recommended in the provisioning guidance documentation, there was no way to actually make this work. So I don't really know how they were deploying this in practice. So what we did is I changed the primary key to use what's called the storage root key. This is part of that provisioning specification. And it's really just a known key at a very specific address in the TPM. And it avoids this owner auth requirement. So it's kind of like a scratch space for everybody that wants to use the TPM without being the owner of the password, which is typically going to be controlled by like an IT organization and not the end user. They have a spot where they can create keys for the TPM without needing like special passwords and stuff. So future work, it would be really nice to do the TPM to seal path. So right now the seals are going unencrypted to the TPM. But at that time, we're assuming that the TPM is in a good state. That was that first to set model. So when you do the seal, that's the set. But it would be nice to be like, I want to do a seal. I want to use this key, this public key to protect it. If you're in a state where you know what you should be expecting in the TPM, so that way we don't have to blindly trust what's there. You know, you could add an option to supply the name of the object or something like that. And I guess we could drop the bind key argument now. There's really no use for it. I just didn't do it. So if somebody just wants to write a one-line patch to delete that, it'd be great. And then I'll throw some thoughts here on SPDM. SPDM is pretty great because it's going to be a generic way to encrypt and decrypt traffic to peripherals. TPM 2.0 devices are going to support it. I've seen some early hardware. I haven't seen anything in the market, but it's supposed to be coming. But you're going to need to have like add support for this and do stuff to get it to work. The TPM kind of already has it, and you won't need the newest hardware to do it. And as you port to different things that may or may not have it, you just know that if you port this design, it's going to work the same everywhere. So I'm a huge fan of adding session support to the TPM and not relying on SPDM until maybe it becomes more widespread. And then in summary, use the feature API if you can. You don't even have to worry about this. It just does it for you. If you're going to use the enhanced system API, do it correctly. Use the SRK. You don't need to be creating primary keys unless you have a very specific use case. And so that's my contact information, and I'll open it up for Q&A. Oh, I thought I was going to get away with no questions.
Oh, sorry. So correct me if I'm wrong, but it seems like you're saying that to verify the public key of the TPM, you basically just read it from disk, and that would probably be like totally unencrypted. So what's stopping an attacker from just modifying the disk and saying, oh, the TPM's public key should be me?
So in the attack, this is why the attack I kind of have questions on, is that somebody's on the bus between the TPM and the host CPU, right?
Yeah.
Well, they don't have access to the disk.
Okay.
They can only be there, they can't be on the disk. That's why I'm saying that's the attack. Now, in instances where maybe your bytes are going across an untrusted boundary, like maybe you're in like a T and the rich OS is moving those bytes to the TPM for you, if you set up that will prevent that rich operating system from being able to tamper with the communications. They could DOS you, but they couldn't do that. Yeah, if somebody actually has physical access to the machine and can get to your physical TPM, I mean, they have physical access to the device, right? That's why this attack, I think, gets blown out of proportion. But the press is an amazing thing.
Yeah, I guess could you like somehow say, oh, here's the public key of all the TPM manufacturers, and then verify it's an authentic TPM device?
So there is a way to do that. So there's this thing called the endorsement hierarchy, and in there is you can create this thing called the endorsement key, and that endorsement key is going to map back to a manufacturer certificate, which so it gets really difficult to do that because there's a lot of different CAs that are used to sign these. And so like if you're in like really, really low level part of the stack and you're trying to walk a cert chain back and verify, like, I think our code base can do it, but it's hard coded for like at least 12 root CAs right now. Now, one thing you can do is some TPMs actually let you remanufacture them. So essentially you take over this endorsement hierarchy and you set the endorsement key. And by changing all that, you could then just issue your own certificates all tied to one root CA, and then you could just have one root CA to verify to, and that would be way more feasible for like firmware when you're trying to do this real down low. It's really difficult to do.
All right, thanks. Good talk.
Yep.
So with V254, man-in-the-middle attacks go away. Is that correct?
In theory.
Okay. So with versions prior to 254, and I know you indicated that this was not intended to be a talk on systemd, but do you know if there's any way to discover or detect if systemd has been compromised for the versions prior to 254? Does my question make sense?
Yeah, it does. I never really thought about like trying to figure out if it's currently being compromised.
Okay.
You'd have to be looking at the communication and then understanding what key was being used, and then maybe verifying that that key isn't certifiable in the TPM to like maybe like the EK or something, like to a key you trust. So there's a way to ask the TPM, be like, hey, is this key actually in the TPM? And you certify that key to another key that you already know and trust. So most people will certify to the EK or something. You can do it with any key as long as it meets the correct attributes. That could be a way. And then you could see, okay, this key isn't in the TPM, but it'd be tricky to do. Okay. Probably better just to upgrade your systemd if that's a attack you're worried about.
Upgrade my system to V254 and hope, in theory, I'll have no man-in-the-middle concern.
Yeah, it depends on like what your attack model is here. So like the classic attack model is somebody on the discrete bus. But if somebody's on the discrete bus, they can probably get your discrete disk too. So, but I mean, there's all sorts of weird ways to use this session encryption. Like we have the ability where you can run your TPM connections over an SSH connection. Mm-hmm. So, you know, when you're starting to cross potential trust boundaries there, properly setting up your encrypted session and not relying on SSH, which is only going to get you from machine to machine, mm-hmm. not inside the machine. Mm-hmm. So.
Okay. Thank you.
Yep. You don't get to ask questions.
Hey, Will. The latest version is 255, by the way. My question is, which PCRs does systemd uses for sealing the password when you're using this?
Okay, at the time of this, PCR policies wasn't there. So it was just pin-based or nothing. During this time, Leonard was adding PCR stuff. I didn't look super closely to it. Yesterday, he just uploaded a bunch of stuff for being able to tie it into PCRs. There's currently 3 different ways to tie it into PCRs right now. Don't ask me what they are. I know the simplest one is just to say, here's a PCR policy, but that gets really brittle, right? Because as updates happen, then your PCR policy is out of date and you can't get to the key. And I'm not sure what he has for a fallback mechanism. Maybe you could unseal with just the user auth or something and grab it. I'm not sure what he did. The newest one is using is essentially using various policy signed type ideas, so you can actually have a mutable PCR policy. But I literally just looked at that stuff yesterday, so I'm not really the right person to ask.
Gotcha. Just because from an attacker perspective, if I can swap out systemd because it wasn't measured into some PCR, that seems to be a pretty clear attack that I just swap out systemd to log whatever pin the user is entering.
If you're swapping out things, yeah, right? And if it's not somehow reflected in a state that's going to get caught by some policy, then yeah, you win.
Cool. Thanks.
Yep. All right, looks like we're done.
Okay, so that goes to sleep, that microphone. So that's the end of the scheduled talks. It's weird being in front of the microphone, in front of the speaker. It looks like there's no more BOF sessions. Did anyone have a BOF session? So that will be it for the Security Summit North America this year. Thanks to everyone who participated, especially thanks to Linux Foundation and to Jennifer and everyone, and the AV folk and everyone who's keeping everything running here, and to the sponsors. So if you are a speaker and you haven't uploaded your slides yet, please do so as soon as possible. And also feel free to grab more stickers there and just redistribute them. Okay, thanks everyone.